Hello. Hello. Everything is audible now. Is it working? Can somebody say
Yes,
yes?
sir. Yes,
Yeah,
sir. But we
I'm
need to
extremely
see your
sorry.
screen.
Yeah,
Yeah.
I'm extremely sorry. I mean, there was all of a sudden power cut, and then UPS somehow failed. So there was an issue. I'm sorry about it. So we'll continue with where we have left. I hope things will work out in better manner from now on. So the point I was trying to make is that we're not talking about the entire laboratory where we have to send our samples, but how we can bring the laboratory to our home, to our bedside, to our neighborhood, so that we can do everything on our own. And that way we can do much better and wider management of our healthcare system, our disease analysis, and so on. That's the whole point to create this kind of chips. So as I move along, I'll show you some of the devices which we have developed in order to create such kind of environment where a user himself or herself can do all this testing. So what you see here is that in order to do that, we have to create some devices, some chips. Like organ on a chip is one very, very important application. We have been working in organ on a chip area where we are trying to mimic the functionality of an organ on a chip, which means that if you talk about a heart or kidney or liver. So if you, for example, give a drug to a heart patient, so there will be some functionality changing into the heart and its surroundings. So we can try to grow the cells of the heart in this organ on a chip application, and then try to understand when we give a drug to the organ, for example, heart in this case, how the drug will respond, how the beating response will change. This is the entire scenario which is changing at this time. So as so on and so forth, you can see how the drug will respond, how we can create a personalized medicine, how we can try to fight against some of the very common disease like cancer or dengue and many other infectious diseases and so on and so forth. So personalized medicine is something which is a very, very important area. I mean, people are trying to do the entire genome sequencing. I hope we all know that human genome has 3 billion bases. So if we can study the entire genome of 3 billion bases, we can try to target the medicines based on the genome, not based on the disease. For example, somebody has a fever or somebody has any disease, and so on. So rather than giving a specific medicine, we can probably give medicine to person A, B, and C, irrespective of the disease. That's what the whole world is aiming for. That is why we call it personalized medicine. So moving on, I try to bring in some of the recent advances, some of the recent news in the area where the microfluidics has created a lot of impetus in the way we are trying to see the things. On the top left side, you can see that how wearable devices have been developed for continuous sweat monitoring, and that sweat monitoring can be done for different applications. A lot of AI and ML based disease classifications, monitoring, and diagnostics, which is happening right now. You can see a simple device. I mean, I have a similar device in my hand. You can see the same similar device, which can be used for measuring multiple biomarkers and multiple ions in your body, especially in the wearable setting. Likewise, you can see many more devices like point of care HPV screening device. And last but not the least, a lot of market is growing significantly. You can see that in next 2 3 years, the whole global market will be close to 35 to 40 billion dollars, and India itself is contributing to 10 to 15% of the entire market. So it gives us a lot of motivation to work in this very interesting area of microfluidics or lab on a chip or micro total analysis system. So moving on, I just thought to bring this very fundamental slide, which the five organs, which talks about the five organs which we all have in our body, and we all know that. So one of the major applications of microfluidics is sensing, diagnostics, or monitoring. So when we talk about the diagnostic and monitoring, typically these five sensors which are God has given to us, like the sight or hearing or the touch or taste or our nose, which smells. But on a normal human being can only use these five organs in a certain limit. And that limit sometimes is way too high, which is beyond the requirement. So that is why you have to develop some chips, some devices, some technologies which can bring down the limit of detection significantly. For example, we talk about the smell sensor. So we all use LPG in our home. So LPG can smell. I'm sure we have seen it in our day-to-day life. But LPG smell, which a human being can sense, which can beyond a certain point. Below a certain point, we cannot really sense. But however, it is extremely important to sense even a small amount of LPG gas because that can also have some side effects to human health. So in order to do that, we have to develop a device. We have to create a specific sensor which can sense much below than the human limit, and so that we can try to address those issues right then and there. So in order to do that, we have to convert that particular smell to a detectable parameter. It can be either in the form of electrical output or optical output or a combination of both. That is why the microfluidics plays an important role. In order to do that, a lot of work is going on over the last several decades, especially in the last few years. A lot of people are talking about novel fabrication methods to develop new microfluidic devices. A lot of people are working on nanomaterials. Now, people are also trying to work on quantum dots and different other kinds of quantum materials. New mechanism, for example, how we can create new electrodes, how we can create new integrated circuitry, how we can use new microprocessors, microcontrollers, and so on. And data analytics is something which is overarching across all the domains in the form of AI, ML, We all know that. So a lot of interventions are happening in developing sensors. And in order to do that, just to give you an example of four different industries, textile, automobiles, energy, and biomedical, you can see that this black and white pictures, which you see right in front of you, these are the pictures or real pictures rather for these four industries 200 years ago, 150 years ago. So that's how people used to create textile, automobiles, energy, like for example, solar photovoltaic and so on. But in today, you can see that everything has become automated. Things are becoming beyond human intervention, and we can create exactly same devices in ultra fast manner, and that too less expensive. But this trend will continue and will get much better, much faster, much inexpensive kind of devices, especially in these four domains. But why it has happened? It has happened because everybody has been working on how we can get much more accurate devices, less expensive, and much faster readout. So microfluidics, just to tell you my thoughts, microfluidics has the key, especially when we talk about the biomedical sector, because we're talking about directly the human lives. We're trying to find out interventions from the human life. So that's why I just thought to bring this picture that ACT or one of them or two of them or three of them will have a huge role to play in next generation of technology development, and microfluidics has the key. So, in this lecture, in this talk, I'll be talking about some fundamental work about microfluidics and especially droplet microfluidics because we can use microfluidics in both continuous manner or we can convert the fluids into droplets and we can understand the microfluidics. Later, I'll also talk about some of the fundamental device fabrication methods. I showed you some of the devices like this one on glass and polymer. I showed you another device on a microscope slide, and top of it, I can see some graphene and some polymer. I will also show you some devices which are made on simple Wattman filter paper, and also I'll show you some devices which are done on textile, a cotton material, and we can create the conductive threads. So all those things can be done in a lab setting, and interestingly, it does not really require huge investment. You can start with very humble investment and you can do on your own. So I'll be talking about some of the methods to create those devices and like hot embossing and 3D printing. And I'll specifically talk about five, six, seven applications depending on the time, how we can use such devices for different scientific applications. And finally, I'll spend some time, a few minutes on what we do, what our lab is doing. So you can see some pictures here. So, and these pictures talking about different microfluidic devices. And as we move along, I'll be sort of spending more time on it. how we have fabricated these devices and how these devices have been used for different kinds of applications. So let's talk about what is microfluidics. I think I already told you microfluidics, fluidics in a small miniaturized micro environment. Whatever I showed you just now, I'm showing you another device right now. So you can see those channels. They are different kinds of channels. They are not the channel which you see in municipal pipelines or the oil pipes. They are very, very small. The size we are talking about 10, 20, 30 microns, the same similar size of your hair diameter, or even little more than that. So the dynamics, the physics, the chemistry, the entire behavior will change in those scales. So we have to work on how we can change the behavior of the droplets or all the flow, or how we can control them, how we can manipulate them. So these three fundamental constraints, or these three fundamental behavior we can manipulate in the microfluidic device. And micro, I'm sure we all know, the small volume. And in many cases, the volume can be as small as picoliter or femtoliter. Because you can see that if the volume is like picoliter or femtoliter, the dimensions is 4 pi RQ, the volume goes by RQ. So you can find out that what kind of dimensions we are talking about. So small size, nanometer to micron scale. And because the volume is small, the size is small, the energy consumption is extremely, extremely small. And that is another facets of microfluidics, and all the effects of microdomain. For example, surface to volume ratio is small, power, I already told you, and so many factors, so many features which microfluidics can give. In these videos, you can see that how a flow can be converted to small droplets. Top and bottom, both the videos are showing you, and each droplet can be a signature of a specific analyte. We can use it as a signature of a bacteria, pathogen. We can use it as a signature of ions in the body, or any other carbohydrates or vitamins and so on. And we can try to understand how we can detect those analytes from these droplets. Likewise, the bottom video shows that how we can manipulate it. We can change the direction. We can make it bigger diameter, smaller diameter. We can flexibly play around with the dimensions when we talk about the microfluidics. So, traditionally, I'm sure that many of you are chemists. So, in chemistry labs, all of have done chemistry lab. All of us have gone through chemistry labs. We do manual analysis. We have beakers. We want to mix two different fluids, two different chemicals. We mix them. We got a bigger fluid with both the constituents, and we can create aliquots in whatever way we want. So I'm sure you must have seen that these aliquots or this mixing depends on many factors. Depends on how do you sort of take them in your hand, how do we mix them, how do we roll it out, how do we create the aliquots. So these aliquots, the entire process is completely manual, and the analysis is also offline. And certainly they cannot be perfect. But when you talk about lab on a chip, we can just create a microfluidic device, and we can inject two different kinds of fluids, they mix them, and we can aliquot them in an extremely, extremely perfect manner. So that is the beauty of microfluidics, which helps us to create the entire process automated with instant analysis, and we can do complete, perfect aliquot in terms of the droplets. So you can also see that we can also use simple Wattman filter paper. We can cut them into smaller arms, and we can inject the fluid from one side, and it can nicely travel to other arms of the fluids. I already showed you some Wattman filter based devices. So these devices essentially either you can cut them, or you can create the Vex boundaries, which can nicely help in letting the fluid travel wherever you want to travel. So these are some of the aspects which are required for microfluidics. But when you talk about the paper devices, because paper has the inherent and inbuilt capillaries, so you don't need to use any kinds of passive components. For example, micropumps, actuators, and valves. But when we talk about some of the glass-based or polymer-based devices like the one I showed you before, it does not have the inherent capillaries. So we need to create we need to use some of the components like pumps and actuators and valves to ensure that we are running these fluids in the way we want them to run. So this is the major difference in the two. The three major laws I want to share with you. which are governing the microfluidics are mentioned here. Once, for the first one is the liquid is laminar. We're not talking about the turbulent flow, which is predominantly happening in oil pipeline or water pipeline. The flow is very smooth. And those of you who are from the mechanical engineering background, they must have heard about something called Reynolds number. And this Reynolds number is typically less than 1,000 or even close to 100 or so. And Reynolds number defines the ratio of inertial force and viscous force. The second major governing law is the surface and interfacial tension. So what you can see here is that if you have a beaker or any other vessel where you have two different phases, like the liquid phase or gas phase, so it can create a nice interface, and it creates a nice surface along with the vessel. So, so we have to take into consideration the surface to interfacial tension between fluid to surface and fluid to fluid if you have two different fluids. So those two aspects nicely need to be taken into consideration how we are talking about the fluid to surface interfacial tension and fluid to fluid forces and tensions. The third aspect, which is extremely important, or which is governed in this entire ball game of microfluidics, is capillary forces. So we have to understand how the capillaries are moving. You can see that these are three examples of three different capillaries with three different diameters. And you can see that how, because of the hydrostatic pressure and capillary forces, how the movement of the fluid is happening in three different capillaries. So these are three fundamental governing phenomena which one need to understand when we talk about the microfluids. Yeah. So I already told you about the continuous flow microfluidics, where we are trying to understand how the flow is happening in a continuous manner. The other way I briefly spoke about is how we are talking about the flow in a droplet manner. So what we can do is that we can also convert the entire fluid into droplets by using a oil and water mixture. I'll show it to you in a upcoming slides. So we can manipulate those droplets. We can toss some specific analyte or biochemical or bioanalyte into these droplets, and we can sort of understand their viability, their movement, their functionality, their diagnostics. So we can do mixing, we can do encapsulation, we can sort them, and we can sense them. So all those things can happen in droplet-based microfluidics. So we can use two immiscible phases, one the continuous phases, where the droplet itself is residing, and the dispersed phases, which is essentially the droplet phase. So essentially, these are another method by which we can try to understand microfluidics and try to see how the droplets will be formed. You can see this cartoon which talks about the formation of droplets in multiple ways. For example, we can use a T junction, we can use a flow focusing junction. Of course, these are the cartoons, and we have done the real work as well, which I will show you a little later. But we can convert the entire continuous flow into the droplets, and droplets can be a signature of specific analyte. Yeah, so in order to develop these devices, and I already talked about continuous flow microfluidics and droplet microfluidics, you have to do something. You cannot just buy the devices, or you cannot really conceptualize the devices and start the work. But we have to do multiple tasks ahead of us. So what this slide shows is that it's like a start to finish approach. When you want to start a new project, you either think in your mind that, hey, I have to develop this. I have to cook food in the evening. I have to make specific vegetable. I have to hit the nail on the wall. So you have to think on your mind, or you draw somewhere, and to ensure that whatever I'm trying to do, it is something in the same line as I really want to do. So initially we have to do start with design and simulation. And typically the microfluidic simulations are done in COMSOL or MATLAB or CATIA. Very popular softwares, especially those who are from the mechanical engineering background. So after designing and simulating and optimizing our design features, we need to go to the fabrication. And fabrication can be in a multiple ways depending on what kind of base material you are looking at. Are you looking at uh, the glass or silicon, or are you looking at the textile or paper or polymer? So depending on that, we can select what kind of fabrication methods I'm going to use. Like photolithography typically is done on silicon or glass. And I'll also talk about direct laser writing. I'll also talk about soft lithography, which is predominantly done on polymer. And laser engraving is done on another kind of polymer, especially acrylic-based polymers and paper and 3D printing. I'll discuss briefly about some of these methods. And detection, we can sort of divide into two major families. How you are detecting optically and electrically. So optically, you can try to understand how the intensity changes. For example, if I change the intensity of, say, glucose or uric acid as a flow through analyte, I can try to understand that the intensity change can tell me the concentration of my analyte. Likewise, I can talk about electrical output, which means that either current or voltage or impedance is the defining factor of my input analyte. And after we can detect that the analyte, we have to do the validation, testing, and need to create a prototype and assemble everything together and try to understand if we can do it in turnkey fashion. If we can just press a button and do the rest of the things. This is the entire value chain to develop the microfluidic device or laminate chip device. So in the beginning, I'll spend a few minutes about sharing my views about the photolithography. So what is photolithography? As the name says, photolithography. Graphy is an art. I mean, photography, videography. So likewise, we have graphy, an art. Litho is essentially it's a very ancient word where people used to use this word to hit on the rock or on the stone. And so you must have seen that people are carving some idol or some specific creatures on stone. What they do is that they hit a hammer on the wall and then slowly make a structure. That's called litho. And photo means in place of hammer, you're using light. So photolithography, if I plug it together, all these three words, is how we can use light to create patterns on a specific substrate. And that substrates can be textile or paper or polymer or glass or silicon, whatever you want to do. Of course, to create the structures on all these substrates, you have to use a different strategy. So essentially, how do we use the light to create patterns? In a nutshell, call it photolithography. So photolithography typically is done in UV manner, and in order to transfer the pattern, we are not using hammer, we are using light. We can use a negative photoresist or positive photoresist. Photoresist means resist means something to adhere to, something we can resist, something we can survive. So light can sort of can does not impinge into those materials. Photoresist. And negative means either light makes it more soluble or light makes it less soluble. So that's how we call it negative and photoresist, negative and positive photoresist. Those of you who have used the old time photographic films, these are very crude examples of the way the negative photoresists are working in today's generation. So very important area, and the entire semiconductor industry is working on these photoresists. They are the building blocks or foundation stones of the entire semiconductor industry, which is running it across the world. And of course, government of India is focusing a lot in semicon. So learning and developing our own understanding in photoresist is extremely important. So you can see that by using those photoresist, I can create this structure on a simple PCB. So what we have done is that we can use some of those negative photoresist films and then shine the UV light and create the patterns. So UV light, wherever it goes, it becomes more stubborn and you cannot really remove the photoresist. And wherever UV light does not go, it becomes less stubborn and you can remove the photoresist. So essentially, UV light is not going to all these places where you don't see copper, and UV light would have gone to this copper places. So this is how you can create structure, and you can sort of make your life very flexible depending on what you are looking for. You can create your structures. Similarly, this example of semiconductor processing on a silicon chip, where you can see that tons of transistors were fabricated on a single 8-inch diameter silicon devices. And the way the process works, you have a wafer like silicon wafer. You create a resist layer. In this case, I'm giving you an example of top positive photoresist and bottom negative photoresist. So essentially, and you can see a kind of a mask which ensure that UV does not impinge through those black lines in both the cases, either positive photoresist or negative photoresist. And after the entire process, in the case of positive photoresist, you get the same pattern as the mask. And in the negative photoresist, you get the reverse pattern of that of the mask. So this is the typical scenario of photolithography. And you can also extend this process to whatever features or whatever patterns or whatever design you are looking for your microfluidic device. So yeah, so this is the process involved. I will not go too much in detail. Probably all of you are invited to our institute, or we can have a separate lecture on microfabrication and photolithography. I can talk more about it that time, but this shows in a nutshell how the entire process works and how we can create different kinds of designs using either negative or positive photoresist. Yeah, I mean, this is a video. I mean, I teach microphysics course, so our students have taken this video, and you can see that we have to play around with some chemicals and chemistry. We have to use some developer solutions because once the light is passed through, you have to ensure that we can remove the photoresist from the undesired portion. That's how all these things are done. So this is developer solution, etching solution, and we can remove the resist wherever you want. You can see this is a simple PCB structure which we have taken and how this PCB structure is used to create the patterns. You can see that nice patterns are kind of evolving on a PCB. And of course, copper will be around after certain processes, and copper will be removed from the processes wherever you don't want it to go. So this is a typical example I just thought to share with you, which can be used to create virtually any kind of structures. Yeah, and then in the previous slides, I have spoken about the photolithography, where I have a mask, which I showed to you earlier. But in some specific processes, you can also do away with the mask, and that is called as a maskless or software lithography. So in place of mask, what you do is that you write the laser on top of the substrate. For example, in this case, this tool is developed from our lab, and you can see that this is my glass slide where I have placed a layer of photoresist, negative photoresist. So essentially, what I will do is that rather than I be using mask to ensure that at some places light should pass and some other places light should not pass, I will just write the UV light on top of it. Either you sort of let the UV light dance on top of the slide, or UV light remains stable and let the substrate dance underneath. So you can design your features on a software, and this is my UV light source, and this is my optics. Optics is extremely important because light should be well collimated on top of my substrate, and substrate is nicely residing on top of a 3D moving stage. You can move it from left to right on a other side, and of course top to bottom. So this way we can shine the UV light depending on what kind of features we are looking at. So this is the typical cartoon of the functionality of this mask lithography and some other features. Probably I can skip that. But the way it works is that you use a film photoresist. You place the photoresist film on top of the, excuse me, glass substrate like this, and then you shine the UV light depending on what you're looking at. So you can see that you can create this kind of structures very nicely. Um, yeah, this is something you can create, and after that you have to sort of make the negative mold of this device. So that's how we use something called epoxy, polydimethylsiloxane, PDMS. So what it does is that we pour a layer of PDMS on top of this substrate, and after baking it, we peel it off. So whatever you see here, maybe I can zoom it. Whatever you see here on my left side, it can be reproduced on the polymeric devices. So one example I have is this device actually. So this is a kind of a PDMS polymer. It's so flexible. I'm just showing it to you. So you can see I'm just forcefully removed this PDMS layer from the glass slide. And then I would have done the same thing on the glass slide on left, and I would have transferred the patterns on PDMS. So this way, what I can do, I can use this device multiple times. I can keep producing these PDMS devices. Of course, plasma is used to bond these open channels onto other substrates, because you can see that these channels are open. If you flow the fluid on top of it, you may not be able to sort of survive because they will leak. So you have to sort of bond it on top of glass or another flat layer of PDMS. So that's where the plasma is important to ensure that the bonding is perfect. So this is how you can create your pattern, your device. This, you can see that I started from a glass slide, and on top of it I created feature using laser, and now I have the entire device, polymeric device, with different features in front of me. So this is how the entire master lithography works. And you can see that we can create different kinds of designs. Like in this case, this slide, this particular microfluid device is used for DNA extraction. So we use blood and we can extract DNA with this device under magnetic fields. And you can see that we have created different kinds of droplet based microfluidic device using the similar kind of approach. So you can play around the droplet, we can change the size shape of the droplets, we can accumulate them, we can toss some specific material in those droplets. So we can do all kinds of things using these droplets after fabricating the device in the way I just showed it to you. And after changing the device dynamics, device shape, size, I can also change the size of my droplets. As you can see from this particular slide, you can generate different kinds of droplets, different viscosity kind of droplets, viscosity values of the droplets, and you can also include or encapsulate different kinds of analytes into those droplets. So far, what we have done is that we have tried to understand what is microfluidics and what are different components of microfluidics. And one of the first component is that how do we fabricate the microfluidic device? And in order to do that, I have shared two major technologies. Number one is the photolithography with the mask, and I also shared the mask-led lithography with the software mask. The other method is hot embossing. We can create a mask actually here, and then using the temperature and pressure, you can create the replica. So basically, this is my master on the left, this is my slave. And with the one master, you can create multiple slaves, multiple devices. But really, I can skip that so that we can focus a lot on applications. And similarly, this is my 3D printing, and I'm sure that in the today's generation, all of us use 3D printing. So this is stereolithography based 3D printing. And you can see that with this device, how we have created structures, how we can create different kinds of microchannels, different shape, size, angle, and very inexpensive manner. We don't need to do any post processing. And in one shot, we can create the entire device. So we can see that this is how the device will look like, and we can inject some electrodes, some optical fibers, depending on the requirement, depending on the downstreaming detection method which you would like to apply with these devices. So, and then I also showed you some of the paper devices. So paper devices, you have to create some wax structures so that liquid remains within the boundaries of, for example, this device is there in my hand. It has the wax periphery. I don't know whether you can see that. Yeah, you can probably see that now. It has the wax periphery, and I can toss my fluid, my analyte within the circle, and I can use them for multiple applications. And the way which we are using it, we can repeat it for many more shapes, sizes, and designs. So this is a crude example how we can create the microfluidic channels on paper. I mean, I may not spend too much time because of limited time available, but if you have any specific question, we can discuss later. And you can also always email me or call me to discuss further. All of them are published work from OpenLab. Um, so this is a quick video which talks about how we can create a mold and how we can create the multiple microfluidic devices. So you can see that this is how we have created the mold. We can cut those polymeric devices using a laser cutter and engraving machine. And those engraver and machine are deposited into wax and those wax will be sort of spread out onto the periphery, and we can put those wax included master in between two paper devices and let it go underneath the roller so that the wax can sort of seep into the paper devices top and bottom, and we can remove the master bit in between these two devices. This is how we can create the wax based patterns onto the paper devices. All published work, and if you need a whole protocol step to step, I can also share with you later. So we can create devices, we can create different kinds of protocols where we can use this nice little paper devices. So now I'll spend the remaining time. We have around 15 to 20 minutes. And of course, remaining 5 to 10 minutes, I'll expect some questions from you. The first one I'm going to talk about leverage a platform for doing the culture and bacteria detection. So you can see when we would like to do the culture and bacteria, I mean, in many of the diseases, especially when somebody has sepsis, somebody has typhoid, some specific kind of fever, doctors always ask you to give your either urine or blood sample for culturing, right? And I'm sure that you have observed that culturing takes sometimes 3 days or 4 days. So doctors cannot really start treating you or giving you the specific antibiotics based on what you really need. So doctors, what they do is that based on their data analytics or past experience, they give you a random antibiotics or close to their confidence level antibiotic. And after 3 days, when the results come, they will start treating you more properly with a specific antibiotic. But 3 days, a lot can happen. So that's why it is important to ensure that culturing can be done in a matter of few minutes or half an hour. And we can try to understand how we can diagnose the particular patient. So that's the whole objective of this work, how we can create a small platform to do culturing and, of course, detect bacteria. So for culturing, the thermocycling is important, how we can do the incubation of the bacteria. So what we have done is that we have used this device, which is here in front of you. And this device can take care of the culturing part. It has the inbuilt incubator. And using the electrochemical analysis, we can find out the concentration of bacteria, which is in front of us. So although I don't have this device with me, it's like a couple of years old. But now we have created this commercial product now. This is already patented and in the process of commercialization. So this guy can do the incubation as well as the detection. And the only thing is that we have to use this cartridge. And this cartridge, which you see here, is again a microfluidic device. So what it does, it has 4 different zones, and each zone is susceptible to one particular antibiotic. So what we do is that we inject a specific pathogen like E. coli or whatever bacteria we try to understand. And then we try to react them with the specific antibiotic and try to see how the antibiotic is helping to change the growth of bacteria. And accordingly, we can be more sure about it. And that process right now is taking 3 to 4 hours because majority of the time we are spending in incubation. But beyond incubation, we can finish everything in less than half an hour. So that's something which we are trying to do. We are trying to incubate the bacteria and trying to understand the growth of the bacteria vis-a-vis to 4 different antibiotics. And of course, this device can be augmented to many, many more antibiotics, like 8 or 10. That's what we're doing right now. Okay, so this is one work. And interestingly, what you see here, whatever you see one device on the left which has the incubation as well as detection part, and on the one on the right side it is something which is trying to understand how the electrochemical sensing can happen, but this device has both the features together. So you can see this is a small handheld device which can be used for antimicrobial studies and how the bacteria can be susceptible to specific antibiotics. The second work, and please stop me wherever you want to because I don't want to overwhelm you with many different examples. Second work is essentially how we can use a simple microfluidic device which is developed on a laser-induced graphene for dopamine, which is a very common micro neurotransmitter actually. So Laser-induced graphene is becoming a very popular method where rather than using chemical vapor deposition, exploration, or other complicated methods, time-consuming as well as not so reproducible methods, we use the laser to shine light and to convert some of the hybridization stage from one stage to graphene stage. And those stages, those lines are known to have much higher conductivity, both electrical and thermal conductivity. So you can see that depending on the software, I can write some lines here. This is my polyimide sheet, which has the sp2 hybridization stage, and laser can convert these stages to sp3, and then that will help me to ensure that we can create a few layers of graphene, and which will be quite predominant in terms of the conductivity. So you can see that we have created a microfluidic device, as you can see in the bottom. So this is my 3D printed casing, and this is my micro channel, and I can sort of throw the device inside, and this is how we can measure the dopamine level using the electrochemical sensing. So in this case, of course, the target was dopamine, but our students have also tested uric acid, cysteine, xanthin, ascorbic acid, and of course, dopamine. So it works very well in a multiplex detection. And you can see some of the papers which are there as a footer on each slide, right? So I'm just giving you a very layman's or very over the top kind of application because my objective is to sort of motivate all of us so that we can be sure that microfluidics can be used in much more simpler applications for multiple applications. The third thing I want to show you is we can also do synthesis of nanoparticles. So we have gone down to the size of 3 to 4 nanometers. And we have also developed the quantum dots using the microfluidic device. So you can see that this is a simple microfluidic device. Unfortunately, I don't have it with me right now. Yeah, I don't have it. But this device has been developed using a stereolithography 3D printer. And it has the four layers actually. And you can see that we have to inject the components or constituents which are required to create the type of nanoparticles you are creating. For example, silver or gold nanoparticles. And of course, while optimizing the flow rate, the Reynolds number, and so on, we can nicely produce very homogeneous nanomaterials. Excuse me. So yeah, so this is something. Oh, sorry. So I'll just start to share with you that how the silver nanoparticles are created. So at the end of the microfluidic device, we can accumulate the supernatant and the outcome, and can collect these silver nanoparticles after going through the entire stage in this microfluidic device, which I'm showing you in front of you. Likewise, excuse me, we have also try to understand this is the entire setup. Of course, there are bulky pumps and so on, but it works very well and in a very, very homogeneous manner. We are also trying to sort of reduce the size and the functionality of these series pumps which are in front of you so that we can make them portable and we can generate those nanoparticles in a much more hands-on or portable manner. So these are the gold quantum dots which we could produce. As you can see that um, we are kind of collecting those quantum dots around 2 to 3 microns, and they work very well in a very very repeatable fashion. And similarly, we have also developed silica quantum dots around 2.5 nanometers. This work is under review, but we can share more details if anybody is desiring. So as you can see, we have developed silver, gold, and silica quantum dots in this same microfluidic device by changing the protocol, by changing the fluid dynamics behavior, and of course the constituents. The next example I'm going to show you is how we can use the microfluidic device to detect ammonia and urea in the blood serum. You can see that this is the main microfluidic device, and we can compare it with the 1 rupee coin and try to understand that we can use this microfluidic device. And of course, use the same method which I showed you before. We can play around with the design constraint which we have. And this is my two inlets, and it goes through these mixing protocols and gets collected here. And then we can sense it right here in this intersection. And later on, we have also created a small lab-based prototype where this microfluidic device can go here. And then we can use other fancy things like a screen or Bluetooth to capture the signal either onto your mobile phone or to your computer.
I think there is some internet lag for Professor Goel. Is it so, or only I am experiencing that?
No, ma'am, is it actually?
I'll
He's not
just call.
audible.
Yeah, yeah. Let me just check with him. So you need to share your screen.
Um,
It's fine, sir. You need to share your screen
yes.
now.
So, um, am I audible now?
Yes, yes.
Okay. I know what's happening today.
That's fine, sir. Only your screen. Yeah, now it is coming.
Yeah, I'm trying. Just give me a second. Today's a bad day. Now, what I've done is that I have, eh, yeah, so, um, yeah. Hello, am I audible now?
Yes, sir.
Yeah. So I was showing this.
So actually, you were telling us the yeah
Yeah,
after this
exactly,
after this.
exactly. Yeah, good that all of you are paying attention. So we are trying to understand that how the pesticide monitoring device can work and how we can measure the one of the organophosphate using the same devices. So I think this device, yeah, this is something like this actually. I mean, which is in front of you actually. So this is a whole prototype now, and we have a startup called Sensom under which we are trying to develop this device. Yeah. So I will show you more in detail a little later. But interestingly, it shows a very linear relationship. And also, we have also tested it with the other four reagents, which basically tells us that other interfering reagents do not really mm, affect the entire process of one specific analyte. Right. Moving on, the next example I want to give you is the this kind of device, which you can see it here. I hope you can see on my camera. So you can see that this is a device where I'm using a 1 inch by 3 inch microscope slide. And this microscope slide, we have, of course, created the electrodes. The device which I'm showing you, the electrodes are a little different than what you see in this slide. But the process steps are quite similar, which I'm showing you to here. So you use uh, a microscope slide, you put a layer of polyamide, you completely engrave it like this by using the CO2 laser, and then you create the electrodes as per your requirements. And this is how the entire device will work and behave in front of you. And we can package it with another capping on a polyamide sheet, and we can flow our reagents as per the requirement. And then these three electrodes will measure the outputs. The one which I have in my hand, which you see it here. Sorry, my video is off. Which you can see it here. It can be more used like an interdigited electrodes because it has the output electrodes. So this is how we can either use it in a three electrode format for electrochemical potential set based sensing, or two electrode format in a more of a IV kind of characteristics. The next device, again, this device was used for uric acid detection. As you can see that uric acid detection is in two different concentration range. On the left, 0 to 100 micromolar. On the right, up to 3000 micromolar. And these uric acid ranges can vary from the application to application for which you are looking at uric acid, either from the body, from the sweat, or from the pesticide, from the food. So different kinds of sources, uric acid can vary. So, but this device is very versatile, which can measure the uric acid value from almost 5 to 10 micromolar all the way till 3000 micromolar. And the next fabrication method is a simple 3D printers, which all of us use. So you can see that we have also created some simple devices. For example, this is my screen printed electrodes. I mean, these electrodes are quite expensive when you buy from open market, but these electrodes are almost worthless. And we have developed a laser induced graphene process. You can see that I have like 10 electrodes in my hand, and in a one A4 sheet, we can create easily 100 electrodes, and we can use them for a variety of applications. The one in the middle is a straightforward FDM based 3D printing, and one on the right side is a photolithography where I can etch the copper on the uh, uh, sheet, on the FR4 sheet, and desired places I can leave the copper places intact, and I can use them again for multiple applications. So you can see that the other method is like the ITO PDMS. I probably may not be able to share everything, but because of time. So you can see that this is the ITO based electrodes which we can develop. And on the one in the middle bottom is the carbon PDMS base. One on the right is the silver PDMS. So different kinds of methodology, different kinds of fabrication protocols which we can use depending on our requirements. The last two applications, I'm going to talk about the electrochemiluminescence kind of devices. So electrochemiluminescence, as the name sounds, electrochemiluminescence. So you provide an electric field, chemistry will start happening, and then based on the chemistry, light will be injected. So the light intensity or the wavelength, both can be an indicator of the analyte concentration. So essentially, what we have done is that we have created different kinds of devices, and these electrodes will help. For example, my analyte is right here. These electrodes can help to create an electric field and ignite the chemical reaction, and then I can take the pictures and I can use those images intensities to understand the concentration of my analyte. We have created a small little prototype which you can see on your screen, and in most of the cases what you see here is that we have tried to use this smartphone, and we have tried to not only use any specific smartphone, we have tried to use a variety of smartphones so that virtually any user can use his smartphone after installing a simple app and start using the device actually. So of course, this is a bit of chemistry, and we have also included develop a graphical user interface, and which has image analysis tool. We can add on some of the machine learning algorithms. We can predict, and we can try to generate and more optimized and more validated results for electrochemical luminescence kind of chemistry. I'll show you a quick video how the entire process works. You can see that this is the graphical user interface which has been developed by our students using a microfluidic device which can be used for electrochemical analysis. So we can generate the data, we can upload the data, and we can use it for image analysis. You can see that each image which is specific to the concentration of an analyte is generated here, and these images can sort of predict multiple information to us. So you can see that these images are generated, and I can use simple tools to optimize these images, and then end of the day I can predict what kind of concentration I'm achieving from a specific image. This is how we have generated this simple graphical user interface. And this device is in front of me. I mean, I just show it to you. I hope you all can see that. Yeah. Yeah. So this is like that device which we have developed, and which can measure many different analytes. And the entire graphical user interface has been built into the device. We just have to insert a small cartridge here, and of course internally the electrodes in the cartridge are sort of connected to the potentials which can be applied to those electrodes, and entire chemical reaction will take place. This is how we are using microfluid device smartly to understand how electrochemiluminescence can work in those devices, and we have also developed a very user-friendly platform into this. So this is what I wanted to cover in my slides about microfluidics and some of the prototypes, some of the fabrication methods which we have created over the last few years. The remaining 5 to 7 minutes, I will talk about our lab. And the reason I thought to bring these slides so that people who have joined this session, they can explore how we can collaborate with each other. If we can help in some way to bring their ideas into reality, we'll be happy to do that. We can also do some real time or hands on or campus based sessions where all of you can visit us, and we can have a residential program for a week or 2 weeks to train all of you for microfluidics and MEMS based devices. So I'm not marketing about our lab, but I'm trying to sort of expose all of you to what kind of facilities are available, and try to sort of motivate you to see how we can work together. So our lab predominantly works on two major aspects to develop sensors and energy harvesters. And the background is the picture of one of our lab. An idea is that how we can align us with the industry 4.0, which means that we can not only develop the prototypes, but also try to incorporate data analytics part, AI ML. How do we develop robust, optimum, and more validated data out of these sensors and energy harvesters? So we work on different kinds of sensors, from biochemical defense, DNA analysis, including PCR, droplet-based analysis, flexible devices. We have developed many different kinds of miniaturized viscometer. I don't have it with me right now. And we have used these devices for organ chip applications, cell growth, soil nutrient detection, water monitoring, and so on. A lot of applications which we have tried to work on. And because we want to develop our devices, for example, this device, it does not need any external power source. So, in order to power these devices, we have to use some miniaturized components. So, in order to do that, we use like biofuel cells, solar cells, and so on. How do we harvest the energy from wastewater or from glucose? And those such energy can be used to run these sensors. In terms of fabrication, I have given you some example, be it 3D printers, direct laser writing, inkjet printer, screen printer, and we can use these devices and we can develop these devices on different substrates, all the way from textile to paper to polymer to glass to silicon. And in terms of the data communication, either optical or electrical methods can be used. We started our work 10 years ago, and now, with the God's grace, we have three major labs, and we can do the entire start to finish experiments and complete prototype which we have developed. All these prototypes I showed you, they are all developed in our lab itself. And our lab have published certainly many papers, and more than that, we have filed many patents, and we have already commercialized around five technologies to many industries. So we have three major labs. One is the MEMS lab, and the picture was there in the watermark in one of the slides. The other one is the wearable, implantable, and nearable devices lab. We call Wind Lab. And the third lab is the printed electronics lab. Some pictures are there. You can kind of appreciate what kind of work which we do and what kind of equipments, resources, and devices which are available in the lab. And some of the tools, some of the equipments, and their pictures and their names are mentioned here. I can share the slides with all of you. I think this session is anyway being recorded, so all of you can see it later as per your convenience. And some more pictures. In fact, you can see that this is an embroidery machine where we can make this kind of textile devices, and you can use them for multiple applications. We have a clean room, a semiconductor clean room, where we can do photolithography all the way till some micron level. We have both class 100 and class 1000 clean room, and many equipments in central analytical lab to characterize and to augment and to automate the entire process. We are lucky to have projects from many funding agencies, and I would like to thank them to support us, to entrust on us and our team to be able to implement many projects. We have been visited by many industry, academic, and government professionals, and we would like to welcome all of you as well. Some of the publications and some journals which are shown here. And our team has also published five major books in electrochemical sensing, in digital and droplet microfluidics, in 3D printing, how 3D printing can be used for microfluidic device development and applications. And recently, we have published one book on MEMS devices, which you can see on the right side. So the idea of this book is that we have put together the entire protocol of around 25 experiments, and every experiment is supported by a video, and video is uploaded on the publisher's, the Wiley's website. So this book is heavily in demand actually, and what we have seen is that in many colleges and universities, the MEMS course is being taught, but most of the time we are limiting experiments just for modeling and simulation. But this tell us that we can create a small MEMS lab and microfluidics lab, and we can create a hands-on experimental flow chain for our own students. And if you need any help, please feel free to contact me. We can certainly help you. How do we devise and design those experiments? Uh, and I think I have just one or two more slides. Um, yeah. So our work has also been captured in media predominantly, and it is very well appreciated, and we have got a lot of traction from this media articles. We have a team of around 8, 9 faculty members from many departments and many of their research acumen, and we have been collaborating extensively within India and outside India. And we have around 35 PhD scholars, around 5 postdocs, and many industry professionals who are doing PhD. And also many of our alumni are working in different parts of the world. This is the list of the some of our alumni, which are working in many different countries and continents. Many of our students have won the awards, and some names are given here. Last but not the least, we have also created 3 startups from the different work which has come out from the lab: Cliome, Pyrome, and Sensom. Cliome predominantly work in biomedical applications, whether it is PCR diagnostics, biosensors, and diagnostics. Pyrome, as the name says, work in optical detection device, as well as some of the devices which can be used, as you can see here, for ultra-fast nanomaterial quantum dot synthesis. Sensom mainly works in environmental and food monitoring devices. Yeah, that's about it. Thank you very much. This is a very slightly older picture of our team. And thank you so much for the attention. I look forward to interact with you and to take your questions. Thank you so much.
Thank you, sir, for such an enlightening and informative session. And I request all the participants to ask the question in the chat box.
I can see a couple of questions already. What criteria govern the selection of nanoparticles or quantum dot size for use in microfluidic devices, and what is the maximum size that can be used without compromising device performance? I mean, I'll try to answer the second part of the question. What is the maximum size? I think maximum size depends on the channel size itself. If your micro channel is like 50 microns, you would like to limit yourself to, I would say, 5 to 10 microns, because the device, the micro particles had to be adhered on your droplets if you are using droplet microfluidics or the continuous flow microfluidics. So the idea of using nanomaterials is not fancy. Is the whole idea is that how we can enhance the surface to volume ratio so that the outcome can be ultra fast, can be more augmented, and we can use it in a more multiplex and mass producible manner. So yeah, so this is the criteria and this is the size window which we can use actually. Yeah, question is, how do medical microchips compare to traditional diagnostic methods in terms of accuracy, cost effectiveness, and accessibility? Gold standard, yes. So I think if any of you or your family have used the glucometer, I think that's something which is becoming very, very popular. In fact, now you can buy a glucometer for a few hundred rupees from Amazon. And there is a small USB drive which is available, and there's a small lancet which you can sort of impinge, and you can put a drop of blood, and then you can use those USB drives to measure the glucose level. So it's nothing new that diagnostic platforms, miniaturized diagnostic platforms are not available, but how do we make it much more accurate and accessible? Cost is something not a big factor, because when we talk about health issues, cost, people think about it, but that's not the first thing to think about. And already the device is available for you for a few hundred rupees. So I think the outcomes in terms of the cost, time, and speed, accessibility is extremely comparable. In fact, is far, far, far better than the conventional benchtop devices. I don't see any other question, at least on the chat box.
Sir, I have one question. First of all, it was very extensive work and really a commendable and inspiring work. And like it gives us inspiration to work in this field. So this that application which you showed where you were able to detect bacteria. So I just wanted to know, like, how does your chip captures bacteria in the sense, like what receptor, any biological molecule that holds the bacteria or something? What is the mechanism?
Yeah, I'm sorry, I did not show the entire process steps to capture the material, the bacteria, or any other bioanalyte on it. There are multiple ways. We can do the direct surface chemistry, or we can do the antibody antigen kind of reactions. We can also do some of the biotin, streptavidin, or NHS chemistry. In this case, we have done the surface-based analysis. We have directly put it down on the surface. Of course, we have done the chemistry. I can share the paper with you. It has the entire protocol which we have used to adhere bacteria on the surface of the microfluidic device.
So do you provide media also to the for growing bacteria, or you
Yes.
just detect? So that comes in your chip only, the
Yes, the
media and
flow through
everything.
chips, which takes the LB broth into the main media, and that's where we incubate the bacteria and then do the growth, try to understand the growth vis-a-vis to the various antibiotics.
Also, one more question. The second application after this, you showed detection of, I think, graphene and then urea, so many bioanalytes together. I just wanted to know how do you ensure specificity?
Yeah.
Yeah.
Yeah, I think I have shown specificity in two, three cases actually, in
Mm-hmm.
not in all the cases actually. So I think, for example, we're trying to understand dopamine or any specific vitamins, right? Chemistry plays an important role as a baseline constituents of the entire analysis. So, for example, I think I showed you one or two examples of I don't know, I hope. Yeah, I think somewhere I showed you that we can. Oh my goodness. Yeah, so I think the specificity comes from the chemistry itself, and we do a lot of bulk testing. I mean, I'm showing you the results only on one slide, but of course, for that one slide, a lot of work which has been done on benchtop for 6 to 9 months is being done, and then it is mimicked in the microfluidic device. So, of course, chemistry has a major role to play when we talk about the specificity.
So that my question is, do you immobilize certain specific receptors or markers on your chip like you need to immobilize or it happens automatically?
No, and it has to be immobilized in many cases. For example, if you're testing glucose, you have to go do the enzymatic reactions like glucose oxidase
Yeah.
and so on and so forth.
Actually, there are a lot of questions, but I think we are falling short of
No,
time.
no, it's okay. We can have a separate
I
meeting, Dr. Sharma. Looks like
I would
you are
like to read
also,
your papers and
yeah.
then get back
I'm
to
not
you.
sure whether you are also working in the same domain. We
No,
can
we
certainly
don't,
discuss.
but it is a really like we are interested in this area, but we haven't done so far.
Wonderful.
And
That definitely we can discuss further. Yes.
yes, sir. Any other question from participants? I think everybody is appreciating.
Thank you so much, and thanks for giving this opportunity. I visit Delhi many times, so if time
Yes, sir.
permits, we can visit you as well sometime.
Yes, sir. We'll connect. Yeah.
Thank you so much, and have a good
So,
evening, and
sir,
enjoy.
one question is
Yes,
there:
please.
how to standardize? Someone has asked about
Let
standardization.
me see.
They have just written how to standardize.
Yeah. I mean, standardization has to be done in two ways, actually. Number one, with your own device, which is sort of specific to a particular biomarker. And number two, you can do it from the standard devices. For example, I talk about PCR. We have developed small devices for DNA amplification. So I don't have that with me right now. So we also have a thermocycler in the lab. Those of you from chemistry background, molecular biology, you can understand. We also have a thermocycler. So we sort of do the testing on the thermocycler as well as in our device and try to understand that how the gold standard is, how do we benchmark it. And all those parameters are available in the open source resources. And in fact, we do a lot of data analytics in the form of ML and try to understand that how we can optimize our own data, which can be compared with the standard data available with the biologists. There is one more
All
comment, I suppose. How to standardize. Okay.
all right, sir. Thank you so much for giving such an extensive lecture on microfluidics and encouraging all the participants to work in this area. Thank you so much, sir.
Thank you so much and have a good evening. Thank you.
Yeah, thank you. So we have
Bye.
another speaker. Dr. Geeta has already joined. Ma'am, are you there? Uh,
Yeah. Hi. Good
Yeah,
evening.
hi, hello, ma'am. Yeah, we actually there was some lag. The first speaker had some internet problems, so it has to be started late. But now we can start. So I welcome you, ma'am, and thank you for accepting our invite to be resource person for this FTP.
Sure.
And
Happy.
so now I would request Twinkle to kindly introduce our eminent speaker. Over to you, Twinkle.
Thank you, ma'am. It's my privilege to introduce our speaker, Dr. Geeta Manjunath. Sorry. So she is a founder and CEO and CTO of Niramai Health Analytics and has led the company to develop a breakthrough AI solution for detecting early stage breast cancer in a non-invasive, radiation-free manner. She is a gold medalist and PhD holder from Indian Institute of Science with Management Education from Kellogg's, Chicago. She comes with over 30 years of experience in IT innovation. Before starting Niramai, Dr. Geeta was a lab director heading AI research at Xerox and a principal scientist at Hewlett Packard Labs. She has received many international and national recognition for her innovations and entrepreneurial work, including CSI Gold Medal Birag Winner Award 2018, and is on the Forbes list of top 20 self-made women 2020. She was the winner of Women Health Innovation Showcase Asia in Singapore, Essential, Vahini Innovator of the Year Award from Economics Time and Women Entrepreneur of the Year 2020 by Biospectrum India. She is an inventor of 50 plus US patent, a senior member of IEEE, and a fellow of Indian National Academy of Engineering. So now, with this, I invite Dr. Geeta to share their insight and expertise with us. Thank you, ma'am.
Thank you very much for the introduction. So what I'll do is, given that we have 90 minutes, right, Dr. Shilpa Sharma?
Yes, ma'am. Yeah.
So what I'll do is I will cover the first part of the talk, and I've requested my colleague to come in and give us second insight in the second part so that, you get to hear both aspects of the technology. As mentioned in the agenda, I'll be talking about an innovative AI-based breast health screening test. And of course, when we talk about, and thank you very much for the opportunity to present in front of these expert, professors and researchers. So, of course, AI, I'm sure you over the full different sessions today and previously, of course, everybody knows about AI, but generally, sort of AI is a term used, to encompass so many things, where so many technologies, where we are trying to kind of automate the process of decision making. And being a PhD in AI. So I've actually sort of used AI much before it became such a big hype and when it was not as fanciable also. So from that time, AI has been thought about as three different methods of doing it. One, use of probability and statistical theory. That is where the machine learning comes in. There's a logic-based, there is one semantic-based. So there are different ways of doing artificial intelligence techniques, right? Different techniques under AI and deciding how the sort of or mimicking how the brain works kind of thing. But most commonly recently, the biggest aspect which has moved forward is the machine learning based one. It's the probability and statistics based analysis, as we know. And of course, more recently, I think the last 2 years or so, the LLMs and GPT has become like a common term now. Every person is using, etc. But of course, we are looking at how can we use this in the context of health. At Niramai, which is a startup I founded after seeing some of my very close relatives die of breast cancer. That's when I said, how can we use some of these AI technologies into the healthcare domain? When we look at using AI in healthcare domain, there are several challenges. We will handle that later. But the different solutions that exist in healthcare typically can be divided into two main categories. One is how it can help in clinical decision support. And second aspect is how it can help in improving the patient's journey, patient experience, doctor-patient connection, mapping, and so on and so forth, in the non-clinical but operational domain. Obviously, we're interested in the clinical domain. And in the clinical domain, the maximum use of or experiments of use of AI for healthcare in clinical decision support has been in the field of medical imaging, because obviously in terms of detecting small abnormal patterns, which are in video or images, is something that we can really train machine learning models to do. And so how do AI and machine learning come together, right? So just setting the context to the work that I'm going to describe. And of course, all of us know what's medical imaging, while we can talk about pathological images or several other types of images also, but the medical imaging that I'm talking about for diagnosis, for example, for diagnosing cancer, lung cancer, one could think about AI on chest X-rays and so on and so forth, right? So, and also, CTs, MRI, all of them form under the medical imaging, medical diagnostic imaging, if you will. And use of AI for that is one of the prominent areas where we are seeing more and more adoption of what we call as software as a medical device, SAMD, right, which is coming in. The reason is because there is definitely severe shortage in radiologists, and these are the images that we can take on seemingly normal patients. And so it can also be used to identify, abnormalities much earlier. Even before naked eye, even an expert doctor can detect, etc., and then they can get onto the diagnostic pathway. There are several sub-problems of use of AI in medical imaging. One, of course, obvious one is how do we classify, let's say, an image that is taken, in this case, chest X-rays, for example, into, let's say, TB or not? Is there potential lung cancer or not? Are there certain specific type of lung abnormalities, like nodules, effusion, etc., which are combination of these will be determined which be used to determine the exact diagnosis by an expert, right? So it could be fine-tuned for different type of classes, as we call it, training with positive and negative samples, etc. AI has also been used in the registration process, like, you're taking an image from different sections, and how do we sort of, when we are looking at inside the human body, right? How do we say that this bone in the first image and the same bone in the second image, right? So the connections, the registration across different views of the body, maybe across time or across like longitudinally during her treatment, or same way you're taking different slices, in both of these, how do we sort of correlate the exact matches of tissue and body so that we are seeing the change over space or time, right? That's something, it's called the registration. So which is actually another set of problems. And the third, there are many, many more applications, but also localization. So can you say where the cancer is, for example, so that there is possibility of doing some follow-up in that particular area, region, etc., etc. So that's another localization problem. Reconstruction problem. You take so many images. How do I reconstruct 3D image of this so that doctors can get a view or a simulated view of the organ and how it's affected? And there are many, many more ways of using AI in medical imaging. So, but one of the most used is where in the first, actually multiple of these cases, so that it can solve a real end problem. Okay, and the reason why it's used and how it will help in radiology per se is, I think many of it's obvious, but just to say the obvious, also it obviously improves the productivity of the radiologist, be it in a rural area or an urban area. And it reduces misdiagnosis. It could be missed cancers or overdiagnosis. Both can be reduced, because even that false positives are also not so great, right? Not so. Sometimes we have objective quantification. What I mean by that is we look at an image and say, oh yeah, there could be some patterns, etc. But then that becomes extremely subjective, different skilled. There's a different levels of skills, and then there could be errors in lower skilled radiologists versus higher. So, but if you had a number or score-based system, then there will be more objective, and then you could also do the tracking like a glucometer at home, right? If it's 100 or 200, you know whether it's diabetes or not, clearly, and everybody diagnosis is correct, almost similarly. But if it's actually, let's say, a litmus paper, light blue, dark blue, light red, and so on, then it's difficult to diagnose. So that's the same kind of objective quantification, which is called radiomics. It's just like we have genomics and all. When we do objective quantification in radiology, which is called radiomics, prioritization of patients in a whole work list, where there are hundreds of patients, which one needs to be reviewed quickly, who are like kind of a triaging of high risk versus this, so that immediate attention can be given to people who are likely to be normal, so that even a week's saving of time in interpretation and report generation also helps, especially if it's MRI or CT. This becomes super important because it takes a long time to actually generate the report there, and so on and so forth. Another, my favorite one, is how AI itself can be used to bridge the gap between the haves and the have-nots, the developed country, where you can use the AI engine or robo doctor, if you will, to prioritize high-risk patients versus that in the rural scenario by just giving the tool in the hands of health workers, right? So, of course, all of us know this in some way or the other, but I wanted to bring this in as a context, not just at the high level, but trying to explain to you or share with you our learnings from developing such a system for one of the largest problems in women's health, which is breast cancer, right? So, so we have developed this engine for detecting abnormalities in the body. This I will skip, but basically that's what we try to do at NIRMAI. And then we have all the certifications and usages, etc., which is what is going to be the primary focus of today's discussion. Of course, we all know breast cancer is a problem, but it happens to be the top problem, or top cancer is a really, really concerning thing. The silver lining is that it is one of the most curable of all the diseases. Nobody needs to die of breast cancer. But the unfortunate thing is that even in countries like India, we see mortality rates of almost 50%. Every alternate lady detected with breast cancer is dying. Last year, 2024, we saw 2 lakh women detected with breast cancer. And same year, 1 lakh women died of breast cancer. So there is this 50% mortality that we see, especially women dying within 2 years, right? Which is the main reason, which is very obvious, is again late detection. People wait till there is a big lump before they come to a hospital, etc. And more so, we see this issue. This is the mortality. That is the number of cancer deaths in different continents, and you see more than 50% of that coming in Asia, from Asia, Africa, another one, and Latin America. So these 3 countries form a major part. And Europe also has a lot of low and middle income countries. So that's another place where, we see a lot of things. So it's clearly a factor of less reduced screening in low and middle income countries. If we can see 70 to 75% screening rate, that is, if you ask a question, any person between 40 and 69 saying, have you ever had a breast cancer screening? The answer would be 70% of them saying yes, so 75% in US and UK, whereas in India, it's 1.3%. And overall in the developing countries. So the clear gap is screening. That is detection of abnormalities even when there is no symptom, and even when the person is seemingly looking normal, right? And the reason why mammography is the default standard, and reason why that screening is not picking up is clearly affordability and accessibility. Looking at the distribution, we would be, we can really see that 50% or 75% of it is from developing countries, because a machine itself is 80 lakhs, and a small diagnostic center cannot afford it. Only cancer hospitals or big multi-specialty hospitals may have, and people may not want to go there for getting the screening done. And so it affects detection rate. It affects the stage at which it is detected, as I briefly mentioned before. And also there is another issue of what is called as dense tissue. So mammography is basically X-ray of the breast. And when you do that, high density, the way we detect breast cancer using mammography images is to look at variations in the density. Like for example, here there is a clear high density lesion. This is the fatty breast, usually seen in women above 55 to 50 to 60 or even above that, where clearly the whole breast is fatty, and when you do an X-ray, it's all black and you'll see a white spot. But every white spot is not cancer, every lump is not cancer, but the radiologist can zoom in, identify irregularity and so on, and then say whether this. The same thing in a dense tissue. If a person has dense tissue, will show up like this. The whole breast appears white because it's just dense things come out white on X-rays anyway. And even the cancer appears white. And this means that there are many, many cases which are missed with the mammogram on a dense tissue. And who has dense tissue? Almost every lady under 45 years tend to have dense tissue. And that's why mammogram is recommended only above 45 years. And even above 45, 50 to 70% of women have dense tissue. So they are recommended an additional test of ultrasound. So this is a scene. And so we wanted to develop a new method where it will be more accessible, affordable, better user experience, as well as works in the dense tissue. And that is what is thermalytics, where we use a simple thermal imaging device or an infrared camera to measure the temperature variations on the chest and convert the temperature map to a cancer health report automatically using a bunch of AI algorithms. First and foremost, it works. We are able to detect even a stage 0 cancer. 4 millimeter is the smallest we have detected, which clearly is anything under sub-centimeter is stage 0. And so we detect very, very early. And so the treatment cost is lower and the efficacy of the treatment is better, etc. It does not depend on the density because we are not looking at the density. There's no X-ray, anything. It's a tissue activity measurement, which is showing up in the form of a temperature map. Okay. When there is a cancer cell which is multiplying at a higher rate, it releases higher temperature, reduces nitrogen oxide, etc. So which increases the temperature of the lesion. Not only that, because it's spreading through the dense or fatty tissue, the pattern around that lesion also is kind of very different. Secondly, every higher metabolism or high metabolic tissue requires more blood flow. And so the vascular patterns associated with the lesion also would be very different. So that's sort of the main principle, and we'll go into more details as we speak more. It is completely radiation free, just measuring temperature, no X-rays and basically infrared rays. This is an infrared camera. So infrared rays are emanating from our human body because we are a heat source, irrespective of whether we are in Kanyakumari or Kashmir, we are at 37 degrees. So the body is sending out that sort of heat waves, so to speak, that's exactly is with the IR. Or some of us would have seen this IR camera during COVID, like, where people are walking into a college or hospital and there are these cameras kept, which are measuring the temperature on the forehead to see whether somebody has fever or not. It's something similar or just a better resolution of it. So and I'll talk about it. It's a no-touch kind of measurement of temperature. You'd have also seen the temperature gun. That is also one-shot temperature. But we use a high-resolution thermal imaging device where we measure 4 lakh temperature points per person. More affordable, and it's very portable, like a simple camera. And most importantly, it is extremely privacy aware. Place it like this, 3 feet from the person. And we have a booth giving the privacy context, like a changing room. So the lady enters, removes her clothes, and she sits in front of the device. And she just rotates on the stool to get the left and the right view. So basically 5 views are taken. Technician outside gives the instructions. So this is the sort of the end user experience. For example, we're seeing it in the video. So she's just sitting in front of the device and just rotating. No one is seeing her when she's not wearing clothes because she's under full coverage, right? So this is the image that is uploaded, or the 5 thermal scans are uploaded. Though I say image, the image is basically a heat map of, we do heat map for so many other, data sets, right? So it's similar to that where a high temperature is given, let's say a color, like here in this case, rainbow palette says white and lowest temperature is blue, etc. So whatever color you're seeing is mapped like a legend to the temperature. But unfortunately, when you are looking at everything which is in the view of the thermal imaging device, a 34 degree and 35 degrees, both are looking red. So we lose the thermal resolution when we are looking at it as a single image of this nature. So we do not analyze the image. We connect up the laptop to the thermal camera and extract the temperature values, which are used to generate this thermal image, and analyze it with the temperature value level or temperature map itself, and then generate a report giving the quantified scores, indicating the level of abnormality, marking the area of likely abnormality as well, and also many times give red, yellow, green to direct a health worker to next level screening if it is red, and so on. So this is what, and the software is the main thing, that is, which analyzes the temperature maps to a cancer health report, is the main software medical device that we have developed. Whereas the camera itself is off the shelf, and so, I mean, it's not sort of really the camera which is doing the job. It's really the software which is analyzing it. So there's several AI models in this, and I'll have my colleague Shiva come in, and so we'll do a double click on this to go into a little bit more details about how do we design an AI-based algorithm, and looking at more as a or a generic problem statement. If any of you want to do this in future, etc., just requested him to join in for the second half. So coming back to this, like, there are about 20 plus AI algorithms behind the scene to convert the temperature map to a cancer health report. The first set of AI algorithms do quality check, whether the image is in good quality, all the images are taken as per protocol, etc., etc. And then we also do like contrast enhancement by just blowing cool air for 5 minutes before the image. So all of that checks whether those were done or not is done as a part of the quality check, because we want to give these devices in the hands of health workers and they can make mistakes and so on and so forth. The next set of algorithms look at extraction of features like vascular structure or hotspot features and others, where we can use those to determine kind of, abnormal thermal patterns, abnormal vascular patterns, etc. So there's about 117 of the thermal features and about 30 of the vascular features are extracted. And they go into different classifiers. Some of you might have studied machine learning for sure. So in that, of course, there's a training module and the testing, cross-validation and testing module. The training is done with images of, here in this case, thermal scans of people who are known to be positive, or we come to know the label later, but basically positive patients and negative patients, and we train, and then you determine the classifier for it. Now, we can either use a completely deep learned model where the full image is fed and it automatically determines what are the features, feature learning is used, and then it gives out a label. But that is not explainable, right? If you ask a deep learning model, how did it do? What is the reason? It's extremely difficult to explain it. But explainability is a very, very important concept or requirement when you are taking this report to a doctor and saying, yes, this is positive. Let's say, like, why? Tell me more, right? What makes you think it is positive? What should I do next, right? So we need to bring in transparency and explainability to it. So what we do is that we have 3 types of classifiers, different scores. I'll go to that basically report where we say this is because of inflammatory action. This is because of the irregular vascularity or asymmetric vascularity between the left and the right side. We see more high velocity blood flow in some part versus other, or milk that's being blocked, etc. So these scores indicate, the different scores we put in indicate the reason why the algorithm feels that there is a possibility of a abnormality. And so finally, we will have much more information about the patient, about her family cancer history, age, their menopausal status, etc. So we take that data also and then give another classifier, which is a simple risk-based classifier, but it now takes these 3 numbers as well. So there are many other things, but most importantly, we have these 4 scores, which are probability scores indicating the level of abnormality. But also because the patient report has to be read by doctors who are used to reading mammography reports, etc. So we kind of also give a score called B score, which is similar to Bired scoring, ultrasound-based or mammogram-based Bired scoring, right? It's a score of 1 to 5, where 4 and 5 is malignant, that is increasing risk, right? 1 and 2 are normal, and 3 is a boundary condition. So that is all. This is automatically given, and that's sort of the main innovation that we have developed. More so, if you want to sort of double click, I mentioned about the hotspot. The thing is, just like a lump in a density domain, we have a concept of hotspot in a thermal domain. And what is hot is different for different people. The way we react to, cool air being blown is different for different people, though all of us are supposed to be at 37 degrees Celsius. So hotspot is a threshold that's computed for each and every person, personalized hotspot threshold, so that anything above that is considered likely abnormal. Now, just like a lump can be benign or malignant, hotspot can be benign or malignant. So then again, we characterize it to say whether it's malignant or not. So that's the hotspot classifier I showed you. Similarly, in the vascular domain, we extract blood vessel structures which are, likely to be high velocity, because they actually show some thermal imprint also. So you can see this is a positive patient who has a lot more blood vessels who are higher velocity in the right side than left side. And so we say there's something going wrong here, right? So it's a screening test. It's not a fully confirmatory diagnostic test. So we will say whether there's an abnormality or not, and then pass it on. If there is a high risk, then we pass it on to other diagnostic worker. So this is the sort of the main aspect of the innovation. And we'll go into more details. So this is a report that is generated. As I mentioned, that 3-4 probability scores are generated, ensemble scores are generated, and finally B score, which is like I said, analogous to the Bired scoring given in mammo, etc., is given, so that the end user feels more comfortable with our report, and it can be used in hospitals and all, without much education to the doctors. Of course, we have to train the technicians on how to take the image, but the doctor should be able to use the report. So that's the idea. And then we also mark the area of likely malignancy in a different color and also show a contrast enhanced image, not fully red and all. We see that, more contrast enhanced so that the follow-up diagnostics or let's say an ultrasound is mostly focused or targeted on the area of the lesion. So there is a more better confirmatory diagnosis that can be done because it is already said this may be the place where the lesion. You remember we talked about lesion localization. That aspect is also done. The several clinical studies performed where we did observational studies, head-to-head comparison. So whoever is going for a mammogram was first given thermolytics, the output was taken, blinded, and the person goes for mammogram. And if person has dense tissue, I mentioned to you, mammo may not find it. So then she goes for an ultrasound also. So we compared thermolytics with mammo plus ultrasound, and if any of them positive or mostly mammo or ultrasound is positive, she went for a biopsy. So like that, we had excellent sensitivity and specificity. We've done several studies, 56 plus publications listed. You can please go through it, but I'll just sort of, talk about one or two of these and go to the next, leave you to read the rest of it. Of course, we kind of worked on it because we really wanted rural people to sort of benefit who did not have access to technology or access to screening in any form. So one of those studies, which I'm very proud of, was conducted in Punjab. Where we did about 15,000 women screening. And this is actually this is Nature paper, digital medicine paper that was published in last January, about a year ago. So 15,000 women screened, out of that 3% were positive. But of course, we don't have the reports of everybody, though everybody we called and checked and so on. They said, gayi thi, kuch nahi tha, aise. But only 150 of them shared their ultrasound reports. Out of it, more than 50% of them actually ended up having abnormality in the ultrasound. And then we were recommended to biopsy. 27 of them finally were found to be malignant. And almost all of them have completed treatment. Now, the question is, how does it compare with hand-based examination, which is used today? So we compare with another study which was done, which is published in Cancer, which is another very big, reputed journal. And there, 50,000 women were screened and 24 cancers were detected with multiple types of CBE, hand-based examination done. And here we were able to get more number of cancers with 1/3 the number of people, which means that, this test is able to detect 3 times more cancer than clinical breast examination. So there are several such sort of results we have. And also we have the regulatory clearance in India and several other countries. Now about 4 lakh women have benefited from the test, available in 22 countries, in hospitals or, rural areas and corporate offices, etc. A lot of big hospitals have actually adopted it. A lot of corporates have screened it. And many of these countries reached out to us and because of the regulatory clearance, we were able to provide the test in all of these places. And in many of these hospitals, it's used for screening women about 25 years. It doesn't depend on like the density, as I mentioned, symptomatic, asymptomatic, pregnant, lactating, no limitation because there is no touch, it's placed further on. And most importantly, it can be used for population level screening and corporate screening can. Of course, we don't want to stop here. We want to sort of take this test to many, many more people. And probably many, many more cancers. And I'm very open to people who may. Suresh sir, I think I'm seeing a lot of money. You can switch off the video. So thank you. So basically, so what happens is that the technology that we are using, where vascularity-driven, cancer detection, is something that probably can detect other types of cancer. So we've done small experiments. If any of you are interested in collaborating with us, that's why I put this more so that not as a vision. We can collaborate for other type of cancers and so on. While I will pause here for other questions, but I will actually sort of lead you to the further under the hood and what other learning can be done in this space to my colleague. But before that, if you have any questions or so, I'm happy to take the questions at this time and then hand it over to exactly what thermal image is and some more details of how we can develop and deploy such, AI-based, this thing is what I've requested my colleague Shiva, who's head of Dr. Shiva Teja, who will come in and explain. So any questions at this stage? Hand over to my...
Ma'am, I have one question. So the
Sure.
concept is very interesting. I just wanted to know, like, what should be the minimum number of cancer cells to raise the temperature which your system can detect? Like,
Yeah, it's a good
yeah.
question. It's a good
Yes.
question. Why, of course, we can't measure the number of cancer cells. What has been found is that, based on thermal imaging, can you hear me? Yeah, is that thermal abnormality. You see, because the use of thermal imaging for breast cancer is not our idea. It was around, there was even a paper in 1976, first time they tried. So what those papers talk about is that this is able to see abnormalities or thermal changes 8 years earlier than a lump appears, right? So it is much earlier. The number of cells, there are certain papers, but I mean, I don't want to quote the exact numbers because it's, I would say, very, we can't be very precise on how many cells per se.
No, ma'am. My question is like if the cancer has just started and it
Yes,
is
early
not,
cells.
the cells are not sufficient to raise the temperature, then the system will
No.
not be able
Every cell will, which is caught up with cancer, will have increased temperature, right? So I understood
Okay.
your question now. The thing is, how sensitive is your camera to catch? How small piece of what we call as pixel can it catch? So higher the resolution, we'll be able to see very, very small change. But the thing is, every increase in temperature is not cancer. You can't just sort of keep watching for any tissue which is high temperature and so on. So that is why we have to wait for a few cells to come together. So for example, in our case, we have detected 4 millimeter lesions, which is very, very early, 4 millimeter, right? Because first stage, you pass first stage when it is 2 centimeters, that is 20 millimeters is the limit for first stage 1. So 4 millimeter is very, very early, 5 times smaller. So that is a proven non-palpable lesion size that we have detected, right? So probably we detected even smaller, but we don't know the size in those cases because they were all non-palpable. Like we could not feel the lump, the patient could not feel the lump. So, but exact number of tissue cells, usually we don't talk about that. We talk about the lesion size in millimeters in this space, in cancer per se.
Okay, ma'am. Also, ma'am, one more thing. Like as far as I know, if there is inflammation in the body, then also the temperature rises. So if suppose the patient has inflammation in the breast, so how do you distinguish the two? Maybe
Correct.
your
Sometimes we
vaccine
can
is
distinguish. No, it's a good point. Inflammation also increases temperature. So sometimes we can distinguish, many times we can't. But our thought process, it's fine. If it is like, for example, an abscess, a serious abscess condition, the doctors say, get them to me. I want to give them an antibiotic. I want to aspirate, right? So that will be needed. It will be considered as a false positive, but from a patient perspective, it's good that we detected, right? But it's not like every inflammation is caught. We also do some kind of irregularity check. And I mentioned, right, we do the analysis of the hotspot structure, which will help us identify if there is, there is some additional. We will pass through. We will say there is high risk. It could be a 4 or a 5 by B score because inflammation can also mask inflammatory carcinoma. We can't say, yes, it is inflammation and let's not do just because there is a very high temperature. It can mask cancer activity also. So our idea is to make sure that when the tool says no, it's a no. That is high negative predictive value. Whereas when we say yes, it doesn't mean it's always cancer, but it is most likely there is an abnormality, which is like cancer. For example, we detected tuberculosis. There also we found higher inflammatory action, but that's okay. We found breast tuberculosis, which there was no other test to find breast tuberculosis. And the oncologists were like very, very happy to find a tool which can, especially community oncologists, were very happy to find a tool which can detect breast tuberculosis. Otherwise, it goes to the lungs very late stage, and that's when obviously the cough and all of that was a symptom. So yes, there could be false positives, it could be inflammation, but that's okay from a clinical pathway perspective.
Okay, ma'am. And ma'am, some questions are there in the chat. So Dr. Saroj is asking how accurate are AI models in breast cancer screening and what type of AI models are used?
Okay, so my colleague Shiva is going to talk a little bit more about the specific type of AI models and how to validate the AI tools and so on and so forth. But let me answer broadly. How accurate? If you saw, I gave that ASCO paper, right, where sensitivity, specificity I showed, right. So that is how you measure the accuracy in healthcare domain, particularly clinical validation or clinical decision support systems. We do not talk about the word accuracy. The reason is because number of people who are healthy is much, much more than the number of people who are unhealthy. Let's say in 100 people, there are 2 people who are having cancer. I'm just making up a statistics here, right? Then you can get an accuracy of 98% by saying no, 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 no for everybody, right? I can just write a tool saying no for everybody. And I would have got 98% accuracy because I was right 98 times out of 100. But I missed the main thing. I missed the 2 people, right? So obviously then it's useless. So what is usually talked about for AI models, particularly in these kind of high risk or low, it's still happening a lot. 1 lakh women dying is not good, but still it is a majorly imbalanced data, right? Only 2 people out of 100, for example, it's called class imbalance. In those cases, we talk about how many among the 2 did we detect as positive, right? That is sensitivity. If you detected 1, then it's 50% sensitivity. So getting, like in our case, 100% screening and 90% overall sensitivity is not a joke, right? So that is that. And then out of the 98, how many you called out as falsely positive? Okay, so that would be like basically how many called out as true negative will become specificity. So essentially, there is a separate accuracy, if you will, number for positive patients, separate accuracy number for negative patients. That is what is called the sensitivity and specificity. Okay, so that is what I already described, and it has been really good. High sensitivity over 90%, specificity is over 85%, I would say roughly. But yeah, there are certain cohorts, like if people have nipple discharge, there may be, so we do the analysis, where did we miss? And then characterize it. When you want to use it in real life, like what we have done, then you have to sort of put in decision rules. If a person has had nipple discharge, so maybe we will anyway pass through, so that, these are future sort of, after the AI models are validated, we kind of, pass it, add rules so that it can be used very confidently and effectively in a clinical pathway. What type of cancer AI models are used? Multiple. Shiva, maybe you have that bigger diagram showing DLML thing, I'm assuming. If not, maybe you can pull it in. But basically, we as I said, we have 20 plus AI models. Some of them are traditional machine learning models. Some of them are deep learning models. And some of them are just image processing, which are feeding into the AI models, etc. So I'll request my colleague to go into like different sub-modules of this whole end-to-end pipeline, where he will describe some of them in more detail. How to validate AI tools in clinical studies? It's a very, very interesting and important question. In fact, I was at a WHO event just 2 days ago, and I presented this one. And before I hand over to Shiva, I'll just flash this. This is a very important. How do we validate? Because people make a lot of mistakes and shortcuts when you validate, right? So there is a sort of the idea to prototype, and then you do the cross validation, etc. And how do we build the AI models itself? Shiva is going to talk about lab level testing. You just take some data and then do lab level testing. So that is clearly one way of doing. But just lab may you got 90%, 95%. You downloaded images from Kaggle. You downloaded images from somewhere. You did it. It's good. That's just sort of just initial, right? But lab level testing is not sufficient to actually sort of lead to the end, user, right? So typically we talk about three types of validation. First one is retrospective validation. You go to a hospital if you want to work on, let's say, X-ray images, right? They already would have X-ray images. There's a validation already available, and the ground truth already available. Retrospectively, you know the answer, but still on a real data, you retrospectively, that is, data is already available. After that, you go back and probably build the model using some part of it, but also test using it. So this is a retrospective validation. Then you do prospective validation, where a lady comes in, she doesn't know whether she has cancer or not. Nobody else knows. Then you do the test and give the result. Unlike an answer sheet, she goes and does the standard of care, right? Blinded manner, and then you do the head-to-head comparison. That's the prospective. Like nobody knows. As and when the new prospect is coming, you are actually validating. At the end of the study, at the end of the sample size, you actually open up the answer keys and then say whether what's the sensitivity, specificity. Next, it is not sufficient to stop there. You want to, let's say, for example, use it. You want to give it to the hospitals. Then the doctors are the users. You want to give it to the field. Then the health workers are the users. So you have to do the testing. Most likely, it's going to be that kind of a funnel thing in real world, right? In the field studies, real world validation. So that needs to be done. And then there again, you check how well the intended users for intended use is being sort of, using it, are using it, sorry. Then the community rollout. If you roll out in the community, what is the, let's say, end user experience? What did the user like? And is there some, changes needed, etc. Everywhere you can come back and then sort of, modify the model, modify the product, etc. And also there is another validation that is usually talked about. It is health technology assessment, where it's not just about the accuracy. It is accuracy to price point. Like what is the price of mammogram versus what is accuracy it gives and how does it. And then of course external bodies do many of the last few things that I showed, because if we ourselves do it, then it is considered as conflict of interest. Like some of the papers also, they look at conflict of interest, right? And in this particular case, this particular technology, we found that thermalytics is 800 times more economically viable, 8x, right? More economically viable than mammography, right? Of course, it doesn't replace mammography, it doesn't replace ultrasound, but because only 1.5%, 1.3% of women are going for a mammogram, this test may be able to screen everyone in India, for example, and send only high-risk women to go to the next level, which is most likely there will be more conformance and people are affording, and the whole health system is able to afford the treatment because it's much earlier also. Okay, so with this, I will pass on the mic to Dr. Shiva, who is already online. And, he will go through some more details of this whole technology and also give you some guidelines as to how to sort of, develop these AI models and so on, right? What are the pitfalls, etc. So you may actually find it useful beyond just this project, right? So over to you, Shiva.
Sure.
So, ma'am, thank you so much for giving us your time and enlightening us with your technology. It was really
Sure.
helpful. Yes, ma'am.
Thank you.
So now
So,
we'd like
Dr.
to
Shiva
welcome-
actually is okay. You'll introduce him, na? Yeah. Okay.
Yeah.
Sure.
So, yeah, ma'am, as you said, yeah. So we'd like to introduce Dr. Shiva. So Twinkle will introduce him. We welcome you, Dr. Shiva. Yeah.
Thank you, ma'am, again for the opportunity to introduce our speaker, Dr. Shiva. He has over a decade of experiencing pioneering AI-driven affordable healthcare technologies to enhance early disease detection, particularly in resource-constrained region. He is the one of the founding member and principal research scientist at Niramai. His expertise spans women health, COVID-19, onchocrisis, diabetic foot, and eye disease. His clinically validated and regulatory cleared innovations are actively assisting doctors in diagnosing disease early across multiple countries with deployments in hospital, government healthcare program, and telemedicine platforms. His groundbreaking research has led 30 plus international publications, multiple book chapters, and 30 granted patents worldwide, 12 US, 13 India, 2 Japan, and 2 Singapore, 2 Europe. He was awarded PhD degree by the Faculty of Health, Medicine and Life Sciences of Maastricht University, the Netherlands, and Bachelor of Technology degree from Indian Institute of Technology, Guwahati. He was listed in Forbes 30 Under 30 India, Forbes 30 Under 30 Asia, VW Healthcare World 30 Under 30 as a young achiever in healthcare. He is also one of the organizer chair for AIIIMA, a conference and a forum with an aim to increase research using AI over infrared image for medical application. With that, I request Sir to take this session over.
Thank you for the kind introduction. Can you see my screen?
So not yet. Now it is fine. Yeah.
Yeah, thank you for the kind introduction and opportunity uh, to talk about how we can utilize thermal imaging for different medical applications and specifically breast cancer detection. So Dr. Geeta has highlighted specifically on how we can use AI-based thermal imaging for early breast cancer detection. What I'll be in is first I'll talk about what is thermal imaging, what is that we measure, why do we need that, and what are the different medical applications of thermal imaging. Then deep dive into some of the AI components of how we are detecting breast cancers with thermal imaging in Niramai. So I think many of you have seen different medical imaging modalities like mammography, CT scan, PET CT, these kind of imaging modalities. But I think very few of you have heard about utilizing thermal imaging in medicine. If you see all these standard medical imaging modalities, they are mostly developed in developed countries, right? And if you see their applicability and acceptability in LMICs, it is very low because these are of high cost equipment. They require high skill expertise and they are not portable. So we can easily provide this screening in the remotest places like countries in India. So that's where we thought, what is the technology that we can utilize for countries like India, where 70% of the population resides in rural locations, where affordability matters. So that's where thermal imaging comes in. The advantage is that they are of very low cost. When you compare this with a mammography machine or a CT scan, it costs like 128, 138 the cost of those machines. These are handheld cameras, so you can easily carry it in a backpack. And as Dr. Geeta has mentioned, we have done thousands of screening camps where we have taken this setup, we have installed it and immediately done screenings. It is completely radiation free. I'll talk about what we measure and how we get the temperature values, but it just collects what is being naturally emitted from a human body. It is non-contact, non-invasive. A additional advantage when we talk about Southeast Asian countries where privacy matters a lot. So thermal imaging provides a non-contact, non-invasive way. And the other use case is since these are of low cost, affordable, and radiation free, we can even use for home monitoring, right? We can use it for monitoring elderly people or disabled people about any kind of sudden complications. We can use, thermal imaging can play because of these advantages. And there are also wearable technologies that we have been seeing recently, where you can simply attach it and we can monitor the temperature profile of different tissues or different body parts. So what is thermal imaging? So thermal imaging is nothing but measure of surface temperature distribution. Every body emits long wave infrared radiation. We just collect it and convert into temperature values. So this is a thermal image that we are seeing. So all it has is all it has is the raw temperature values that are recorded in a non-invasive, non-contact fashion. Like for example, the temperature here is around 35.5 degrees Celsius. So like that, for each pixel, we will have raw temperature values, unlike color values that we typically see in visual images. So how does it happen? So as we said, every object emits the long wave infrared radiation. The thermal cameras collects all the energy that is emitting. We typically get three type of energies. One is the radiation emitted by the body, the target object. One is if there are any surrounding heat sources, the reflected temperature that comes in. and one is the other one is the atmospheric energy. So the thermal cameras capture this entire total energy, and using thermodynamic principle, you can obtain the temperature of the object by having some of the parameters as known parameters. So like, if you set the emissivity, reflected temperatures, and atmospheric transmittivity, and these parameters, you would be able to accurately get the temperature values. And this is very important because when we talk about the temperature value computation here, some of these parameters, for who want to work in this area, these parameters are absolutely critical if we want to measure the accurate temperature values. So, like for example, emissivity is, if you are measuring for a human body, the emissivity value is set to 0.98. Reflected temperatures are typically obtained by the heat sources that are nearby. If you ensure that there are no heat sources, you can set this temperature value to 25 degrees centigrade. And atmospheric transmissivity and atmospheric temperature, since we are talking about the medium as air, this will be close to 1, and this parameter don't contribute. So these are the two main parameters. If one sets it properly, we should be able to get the accurate temperature measurement. Now, what we are capturing, or what the thermal camera is measuring, are temperature values, right? These are like 21.3 degrees centigrade, 21.4 degrees centigrade, or if the sensitivity is 50 millikelvin, you will see multiple decimals. These are hard to visualize. So for the purpose of visualization, we employ color palettes. We call it a pseudo color palettes. So these are 4 standard color palettes that we typically use in thermal imaging, wherein the concept is that the lowest temperature is assigned to the lowest row of this color palette, and highest temperature is assigned to the higher max row of this color palette. So each of this color palette has its own advantages. The rainbow color palette, which you are seeing, helps in understanding the focal temperature patterns. The grayscale and inverted grayscale patterns are very useful if we want to analyze the vascularity. Like you can see clearly the vascular structures in the neck region. Iron hot palette is not a standard medical palette, but it's a standard thermal imaging palette, which is typically used in industrial applications. So with this, what are the different clinical applications with thermal imaging? As Dr. Geeta mentioned, breast cancer is one of the prominent use case, which has been there since 1960s. So anyway, I will be talking more in terms of what are the different AI techniques, and what are the reasons for why we can detect breast cancer. And Dr. Geeta has also covered. So next is diabetic foot ulcers. Diabetes is increasing, and more younger women and younger population is also getting diabetes. And if you see the statistics, 19% to 34% of population with diabetes will develop some kind of diabetic foot ulcers during their lifetime. And 20% of them ultimately have to go for amputation, wherein we have to remove a section of the leg or the full leg itself. If you see the current technologies that are there for detecting diabetic foot, it is simply tuning fork or needle pricking, which is available in metropolitan cities, and it is not, many people are not aware of this, and it is highly subjective. There is no imaging modality or the quantified way of identifying this, which makes it challenging for early detection. So since we are again talking about the diabetic foot ulcers, which basically affects the vascular supply. And the foot region, we have the vascularity close to the surface, subcutaneous tissue. And these ulcers create pain. And if there is any kind of loss in blood supply, we can clearly see it as a cold spot, right? So with this, there is a lot of research on how we can leverage thermal imaging for diabetic foot ulcers. So the advantage again here is we can make this entire setup completely non-invasive, affordable. We can deploy this in a remotest area, and then have these thermal scans and automatically identify whether there is any kind of foot ulcer or any kind of loss of sensation that is happening, and identify these in their early stages, so that it can be a simple OPD surgery that can be done, and we can reduce the number of amputations that are going as of now. So head and neck cancers is another growing use case where thermal imaging has been useful in identifying different abnormalities related to head and neck. Again, the head and neck, when we talk about the vascularity is superficial, we can identify the vascularity, and organs like thyroid or oral cancers are very close to the surface. So this allows the use of thermal cameras to identify any changes due to malignancies or due to any kind of abnormalities. So there's a research that talks about how we can utilize this for oral cancer detection, how we can utilize this for thyroid cancer detection. So these are some of the growing use cases of how we can leverage thermal imaging for head and neck cancers. So this is one of the research area which Niramai has worked on. Onchocerciasis is one of the leading cause of blindness in African and South American countries. So what happens is it is transmitted by a black fly. It is a larva, which when injected to human body, it can grow up to 15 to 45 centimeters, and it can lay 100 to 1000 eggs per day, which again grow, and it can reach to eye and then cause blindness. And because it can travel throughout the body, it causes skin irritation, skin diseases, all these things. So the standard way of detecting onchocerciasis in these countries is taking a tissue sample. So they take multiple tissue samples at different locations and send to a pathology lab. And we found out that there is only one pathology lab in our entire African continent where this has to go, and they analyze and then tell whether there is something or not. So this is not scalable at all. So what Bill and Melinda Gates Foundation wanted to see is, can we utilize some kind of imaging modality which allows in mass screening. Again, since onchocerciasis is a subcutaneous, many of these nodules, they are just beneath the skin tissues, and they have high resource constraint where they draw more blood supply. So we thought, can we utilize thermal imaging to identify this high metabolic activity? So we have done this initial pilot study, and the results are very promising. And we have even open source these data sets. So I'm just keeping these open source data sets next to it, so that if somebody is interested in trying this, you can download these data sets and try the applications of thermal imaging for different diseases. So the natural application is any kind of injuries, all right? So whenever there is any kind of inflammation or pain, it increases the temperature around it. So even if it is a sports injury, or we are talking about any kind of burns, what is the degree of the burn, all these things, thermal imaging is a natural use case where we can detect these injuries. Apart from it, we can measure the respiration rate with thermal imaging camera, which allows in non-invasive monitoring. It could be specifically useful when we are talking about um, child, for babies monitoring. Instead of having multiple sensors attached to their skin, we can have a thermal imaging to monitor them continuously. It's also found to be useful even to identify the mental stress detection. During COVID-19, we have I think many of us seen during the public places. It has been useful for um, understanding whether there's a fever or not, basic screening, and further, to comply with the guidelines of mask, wearing mask or not. The challenge with visual imaging cameras are like you need to have a minimum illumination, all these constraints. But since thermal imaging, is just measuring the long infrared radiation, there is no illumination constraints. So that was one important use case that we had also worked on during COVID-19. Pain management and treatment monitoring are other natural extensions. Again, both are inflammation, which causes more vascular and more metabolic heat pattern, which again can be picked up by thermal cameras. So veterinary medicine is another area. Unlike humans, animals can't express pain. So it's very hard. We can't completely scan the animal directly when we're talking about like horses, right? It's very hard. So that's where again thermal cameras can easily point out any localized heat patterns which are at high temperatures. That can help the veterinary doctor to have specific treatment or diagnostic regime that they can recommend. Otherwise, it's very hard to understand, where the problem is when we are especially dealing with veterinary medicine. So these examples shows how thermal imaging is changing the future, wherein it is allowing us to use more affordable and scalable solutions for LMICs in not just one particular area, as Dr. Gita has pointed out. We have multiple use cases around it, and over the last decade, we have seen multiple people working on all these different problem statements, and we have also started open sourcing these data sets so that there is more research that can grow, and it could benefit countries like India. With this, I'll move on to how we utilized AI for improving breast cancer detection in Nedamite. Before that, I thought I can just give a overview of what is the journey, specifically when we have some kind of medical imaging problem, what all it takes to take this into clinical practice. So the first and foremost step for anyone who is working in this medical imaging plus AI is we need to identify a problem statement with true clinical need. It seems very obvious, but not all problem statements that we have might have true clinical need. For example, we can think about screening tuberculosis with PET-CT. Though you might get very good accuracies, it is not clinically viable solution for screening because of its cost, because of its radiation, and because of the competition that is already there. So that's why it's important, we need to understand what is the problem statement is going to serve, how is it going to improve patient or clinician experience, and we need to understand what are the risks and benefits of the proposed technology when compared to the what is available outside. This is crucial not just for our understanding, it's also for even as per regulatory, it is one of the foremost steps before planning for development. The regulatory will suggest to have this risk benefit analysis to be done in the beginning itself. So once we are sure that yes, it has more benefits than the risks, the next step for any kind of AI problem statement is to get data. We can collect from direct data, or we pull the data from multiple open sources. So the challenge with medical imaging is we always end up with low variety, low volume. It's because many of these data sets, when they collect at single site locations, which allows for low variety. And because it's not easy to collect data, you would always end up with low volume. So it's always better whenever we work with this problem statement, not just to download the data set that is accessible, try to pull out as many data sets as possible because it gives us more variety and more volume. And one of the main aspect which we see when we download these kind of data sets outside is many times we don't question the ground truth that these data sources provide. But that's very critical when we are developing the model because we have seen many of the open source data sets where the labels of the data is annotated by a single radiologist. When we talk about cancer, right, not a single imaging modality is 100% accurate. And even the standard the techniques are only 90% accurate. And this we are talking about very senior radiologist performance. And many studies shows that if it is a junior radiologist, the performance can be as low as 60%. Now, if you're downloading this, many times we just ignore how they're getting the ground truth. Are they using a radiologist annotations, or are they taking the pathology confirmation, which is the ultimate ground truth, or are they doing multiple tests to correlate? So many times we do not question it, but it's important that we should question it in the beginning because garbage in is garbage out. If you don't, if the labels are not consistent, even though your lab test results are 98%, when you deploy it, you would end up getting poor performance. So there are multiple ways you can tackle this. One is if the data sets are typically used, labeled by a single radiologist, maybe one can employ multiple radiologists and take a weighted voting or some kind of voting mechanism to figure out these labels. And as Dr. Geeta has mentioned, the challenge in medical imaging is like imbalance in data because the incidences are low. When we're talking about cancer incidences in asymptomatic population, it could be 1 in 100, 1 in 1,000. That means you have to screen 100 or 1,000 people to get 1 or 2 cancers. So imbalance is a main issue. So you need to have mechanisms to fix this imbalance. And also another aspect, another bias. I'm talking about this different biases that we might get, right? So when we download the data, we also need to understand whether there are any inclusion criteria conditions. So, for example, if you're downloading a data set that is collected in a symptomatic cohort, right? It's a cancer data set, but all of the population have some kind of symptoms. If you just use this data set and you develop this model, but if you forget that these are symptomatic population and apply this model on a asymptomatic population, you would end up giving high scores or the very low scores for asymptomatic population. So it's important that you identify what are the limitations of your models and what are the biases that you have. Once you figure out, you can have different AI models developed to mitigate these biases and evaluate them on independent data sets. And as Dr. Geeta mentioned, explainability and interpretability are key to clinical integration. You need to start during AI development itself, how I can make the models explainable and interpretable. Because many times we see that people try to get some accuracies and then try to explain the results. Because that will not directly express. It's always better you start it from the beginning itself, that how I can make the models more interpretable and explainable for the doctor, so they're more comfortable using this system. Because if you simply say yes and no for an image that there's a cancer or not, but if you don't explain, the radiologist won't be confident in concretely giving this decision to a patient. And again, as Dr. Gita mentioned, we need to understand different performance metrics, right? For different problem statements, you might see different performance metrics. So one has to look at it like accuracy is not a good metric when we deal with these kind of scenarios. Like, you might have to go with sensitivities, specificities, and estimate model utility. It's important that, at the stage of model development itself, you need to understand where the model works, where the model fails. This is critical because the next step after AI development is getting the regulatory clearance. So for the regulatory clearances, you need to do clinical studies. And for the clinical studies, you need to have a clear objectives. If you don't know where the model fails, and if you have a generic objective in the clinical studies, when you have the population arm that is coming from in this non-working arm, you would have again poor performance. So it's important you identify where the model works, where the model fails, and it's absolutely fine that no one expects that the model should be generic and it has to work well for all populations. If there are limitations, you can be upfront and you can mention that. It's absolutely fine. We can take the example of mammography. The mammography models, they typically say that the performance is poor for dense, but if it is a fatty tissue, the performance is good. And they can give the density score. So it's more like that. It's, one need to understand that we don't have to try and develop the AI models that solves all the issues, but it's important we need to know where it works and where it fails. And as Dr. Gita mentioned, one can do multiple clinical studies in order to roll out this into community screening. And the final step is clinical integration and real world surveillance. So the job is not done once we just got the clearance and then we deploy it. It's important that one has to work with doctors to understand what they are facing, what are the challenges they are facing, and try to improve that so that it increases the clinical adaptability of the solutions. Many times, we have seen in some of our experiences, the main drawbacks or the main limitations of doctors not adapting are sometimes very small things which we miss during development. So one example I can give is during COVID-19, we have developed this X-ray based COVID-19 detection using WhatsApp. And one of the challenge we faced was we saw many doctors are getting onboarded, but they are not sending the images repeatedly. So we tried to contact them and asked what are the main reasons why you're dropping out. So we found out that some said that, I gave some random traffic image and the model still generated the report. And some said that, I sent some images and the model didn't give good results. When we looked at these images, right, we understood that it's important that, when we develop this pipeline, somehow we missed these image quality checks, right? Where because it was during second wave and we immediately released it, but we thought everyone would upload the proper images, but many times it could be the way of testing, the way of getting confidence of the system, or it could be not knowing how to capture these images. So we immediately developed this pre-processing pipeline, and that has gave more confidence to the users. And the maximum peak during that time we saw was like 3,000, 4,000 users using this service per day. So it's important that we need to understand once we deploy, work with doctors where the model where they're facing issues and continuously improve it. With more and more data, we can always fine tune the performance as well in case the performance is low. So Dr. Gita has mentioned about the importance of the breast cancer, why we need to detect in the early stages. Just to give again the high level view of why thermal imaging is the existing technologies of X-ray mammography, which is a gold standard. It is mainly designed for high-income countries or the where the or the metropolitan cities in India. because of its high cost, high infrastructure dependency. It is not easily portable because it requires proper shielding because it uses radiation. It requires dedicated power supply. There is a manual expertise, and one of the other challenges is disrobing in front of technician, which is a challenge in Southeast Asian countries. And MRI machines are also very costly. They're not easily portable. All this makes the screening in rural India very challenging. Not only rural India, any kind of LMICs. So that's where again thermal imaging is having multiple advantages. So instead of currently detecting hand examination in rural India, the proposal is to how we can utilize the heat thermal activities to detect cancers instead of detecting with hand. So we are getting this kind of thermal images. What are the, is it easy to interpret? If so, why we haven't seen, like, even though it is in 19, since it is existing in 1960s, why this is not clinically adaptable, right? If you see that both the images, what you are seeing are the same, are the thermal images of a same temperature array. As we said, thermal cameras captures the temperature array, and we select some, we use temperature color palette. But in order to tell what is low and what is max, it is little subjective, right? If you take minimum and maximum temperatures as image min and image max temperatures as the min and max of the color palette, what if there is some background switch or some object because of which the temperature changes, right? So that's what this tells. So if you select 25 degrees centigrade as a lower limit and 39 degrees centigrade as upper limit, this image looks perfectly normal. You don't see any kind of abnormal heat pattern. But for the same thermal image, if you select 28 degrees and 36 degrees centigrade, you see a hot spot. And this is in fact biopsy confirmed malignancy. So that's the main challenge. The temperature values which we see are very minute variations, and we rely on false color palettes. So it requires very high expertise to analyze this. And the other aspect which has changed over the years is the way how we measure the temperature values and basically the hardware technology. Now it's easy to measure. We used to use cooled sensors, cryogenic sensors before. Now we can use uncooled microbolometers to measure the temperature values. So it has miniaturized a lot, and the temperature sensitivity has increased a lot. We can measure now 50 millikelvin. So that's one of the reasons why manual interpretation couldn't pick up. And if you really want to measure this minute temperature values, AI is the leader in this, right? We can understand these temperature variations and then characterize it into a normal or a benign or a malignant heat pattern. So as Dr. Geeta pointed out, why detect, what are the main biology behind detecting breast cancer with thermal imaging is it's nothing but uncontrolled cellular growth. From the beginning of the tumor cells behaving in, abruptly, which is like uncontrolled cellular division, they require resources. And in the research, it is found out that even before forming it as a mass, the tumor cells employ the existing blood vessels to feed more blood. Now, when they are drawing more blood and when they're creating new blood vessels, they increase the heat pattern. And since many of these are superficial in nature, these might have more heat pattern compared to the surrounding tissues. So that's where thermal imaging can pick up these variations, and we can use it for further classification. So yeah, these things Geeta has covered. So just to give a brief overview is how the screening happens is when technician when a participant comes, technician explains how the screening is done. We cool the participant for 10 to 12 minutes because they might be wearing tight dresses They might be coming from a hot environment. We need to stabilize them so that any kind of superficial heat patterns get erased and the patient is in thermal equilibrium with the surroundings. After that, we capture 5 different views because if you take single view, we might miss the heat pattern coming from the sides. So to cover the 180 degrees of the breast region, we capture 5 different views, uploads it, and doctor verifies and generates the report. So these are the different AI ML modules. Often when we talk about medical imaging classification, it's not a single model that does the job. We will have a series of machine learning modules to ensure that we generate more accurate report. So in the same fashion, for us, we have multiple modules. So we have a few ML modules that are more about checking the quality of the image. Again, garbage in is garbage out. If the images are not captured properly, you would end up generating incorrect or inconsistent reports. So we have we have different image quality checks, followed by different segmentations or localization, where we would like to identify different characteristics. Like in this scenario, we might want to identify, because we're capturing the image from neck to abdomen, we are interested only in the breast tissue. So the first and foremost task is to identify the breast tissue, followed by different localizations of the tissues that are more more interested for a radiologist. So when we ask the thermologists, they typically look at 3 characteristics. One is focal high temperatures. Whenever there are focal to high temperatures, they want to understand what's the temperature increase, how they are, what is the symmetry. They look at the vascular activities, and then they look at the nipple areolar complex. So once we understood that, we realized that in order to make our algorithm more easily explainable and interpretable for the radiologist, we also need to replicate the same process. So we have done similar kind of segmentations, and then we extracted interpretable radiomix features, which basically characterizes hotspots so that the doctor can know, immediately what the temperature increase, how the boundary, how the symmetry. And then we individually classify, so we know that which characteristic is contributing to the malignancy. And then we try to generate a final scoring using all these features that we have extracted. So in the interest of time, I will quickly cover this at high level. Dr. Geeta has also covered this. So one of the questions that we had was what are the different modules that we use for detecting cancers. So in this one, the image quality checks, we have the combination of deep learning and simple image processing approaches that could address our quality issues. So typically when we talk about thermal image capture, we foresee 3 issues. One is one of the main issue is that incorrect labeling of the views. Many times the technician captures right view and labels it a left view or vice versa, right? So in this scenario, the technician uploaded a right breast image for left view, a left oblique view, because the right breast of the patient is on the left side of the technician. So what happens with this kind of error is, instead of saying malignancy is on the right side, you would end up saying malignancy in the left side, and patient will go for a follow-up on the left side, and you might end up finding no cancer. So in order to avoid this, we trained again a deep learning model, which is inspired from ResNet, and we were able to classify, given an image, what is a view angle, right? Or which class it belongs to out of these 5. So the accuracy is as high as 98, 99%. And the second quality issue that we have seen is focus, because we're talking about thermal cameras and we have the lens. The common issue is if you don't focus properly, the temperatures gets averaged out and you would see a blurry image. So we have a simple focus share, because this is easier problem. We don't want to complicate it. Whenever there is a improperly focused images, you would end up seeing the edges as blurry. So using that logic, we have simply developed an image processing algorithm to quickly do that. For cooling check, we monitor the graph, and then over time we try to see what is the mean body temperature. We track it. That allows us to tell when is the right time to capture the image and whether the cooling has been done sufficiently or not. Now the task is to identify different region of interest segmentations, and one of the main tasks for us is to identify the breast tissue, because when we capture the thermal image, we have a lot of unwanted regions like abdomen, neck. And the challenge with breast segmentation thermal images is, unlike other segmentation, rigid segmentation, there are no concrete boundaries. Even when we give the same image to experts, the segmentation could be different because there is no rigid boundary on the top. So when we did this exercise, the inter-dice correlation is around 91 to 92%. So what we have done was we had tried to propose a new loss function that could take care of this. And then we trained the encoder-decoder architecture to automatically identify the breast tissue given any view. So that has given us around 91 to 92% dice index, which is as close as to the human concordance itself. And as Dr. Geeta has pointed out, instead of simply looking at is a black box, yes or no answer, we wanted interpretability and explainability. We have utilized the vascular features, which Dr. Geeta has covered, and different radiomics to characterize the cancerous activities. And a detailed report is, how it looks is this. We have different hotspot score, ARELA score, which basically tells that, okay, the score is high, mainly hotspot score is high. So which means the contributing factor which we're seeing in this case is the focal temperature increase. The vascular activity is also high. So accordingly, they could suggest the next steps. And we also give auto text generation report, the the conclusion as well for the radiologist, which the radiologist can modify it. These are some of the publications which Dr. Geeta has already talked. And these are the regulatory approvals and quality certifications which we received after doing multiple clinical studies. And yes, these are the peer-reviewed publications. With this, what I just want to conclude, want to say and conclude is that thermal imaging has numerous applications that we are seeing over the last decade, not just in terms of cancer detection. It can be used for any kind of skin disease detections, skin malignancies. So there are a lot of use cases that has been coming up, and because this is an imaging modality which one can which one can easily buy even in an Amazon. These imaging devices are available. One can easily try get this. It's completely safe. It's non-invasive. There are no health risks associated with this. We would be able to develop more and more innovations over the next 5 to 10 years. Thank you, and happy to take any questions that are there.
There is one question in the chat box. Please clarify a doubt. Can CNN models be used for real-time medical diagnosis, and what would be the potential impact on patient outcomes?
Yes, I think definitely. As we discussed, CNN models are utilized. Even in our scenario, we had used multiple convolution neural networks for detecting vascularity, for detecting breast region. The important aspect is we need to give a confidence to the radiologist, right? We need to understand who is our user, and we need to have thorough testing. For CNNs, what we have typically done in our use case is we used it for localization purpose. So whatever we localized or whatever the algorithm has predicted, we show it to doctors and technicians. So whenever algorithms are doing any kind of mistakes in predicting wrong breast tissue, we have a user in the loop who can verify this and correct this. And in the same fashion, many people have been using grad camps or some kind of class activation maps in order to understand where the model is looking, and then give some kind of cues for the radiologist that, okay, this is the model that is looking, here it is looking at. And using that, doctor gets more confidence in, relying on the diagnosis. And sometimes, we talk about screening at remote locations where the user is maybe a technician. In that scenario, we might not need to explain because it's used for triaging purpose. So it depends a lot on the use case, and CNN models are heavily being used nowadays for medical image classification. But I think we need to understand where we are using it and how we can make it as transparent as possible so that the decisions the CNN models generate, one can understand and rely on it.
Any other question we have? So just one personal question, how much is the cost of Nirmay Analytics for this scan? Like,
Yeah,
if you want to compare it with the market
right.
test.
The device cost, when we speak about the cameras, the thermal cameras can vary from 4 to 8, 4 to 10 lakhs, right? When we compare this with mammography machines, they start from 1 CR to 3 CR. And when we talk about MRI machines, they can cost around 5 to 8 CR. So if you compare with that, the device cost is almost 128 or 138. And we're also trying to see, can we utilize the low-end cameras? Nowadays we have the mobile attachment cameras, which cost around 50, 60,000. That's it. Less than the mobile phone cost. So we are trying to explore if we can even use that, because that could help in self-screening, or we can even give it to gynecologists. So the cost of the device itself is very low compared to the standards. Now, what is the consumer cost? It depends on where they are getting the screen, because this is a decision taken by a hospital or the screening camp organizer. For screening camps, it's often free because it's sponsored by some other third party. For a hospital screening, it is usually charged by the hospital.
All right, Dr. Shiva, thank you so much for such a detailed conceptual talk on thermal imaging, and thank you for your time. And with that, we end our session 2, and tomorrow we'll meet at 6 p.m. for day 4. Thank you, Dr. Shiva, and thank you all the participants for your time and attendance. Thank you.
Thank you, everyone.